the term environmental risk assessment is replaceable with ecological risk assessment. They are talking the same thing. When we talk about environmental, also include human. When we talk about ecological, sometimes we focus more on wildlife, the environment more. But in some cases, we also consider human health risk. Okay, now, since our center, our laboratory focusing on marine pollution, so in this presentation, I will focus on chemical pollution in aquatic environment. So, as I said before, now we manage the environmental quality based on environmental risk, okay? So the question is, how much can we pollute the environment without unacceptable consequence? So we have a rainbow of different level of pollution. If we aim to very, very clean water, then we have to have a cost to pay. Of course, we can use a very advanced reverse osmosis to clean everywhere, to clean all the water, but the cost is enormous. I mean, even Hong Kong is quite well-developed city, but we couldn't afford to have a tertiary water treatment for whole Hong Kong. Then we rely on secondary wastewater treatment. Then the effluent still contain a lot of pollutants in the water before discharging. So then we have to draw the line how much we can pollute without the unacceptable effect is the basic concept for modern environmental management. There is no way that we can achieve zero discharge nowadays because of the cost. And also another problem is long-range transport of pollutants. The pollutants can come from the sky, from the atmosphere, and also from the marine current. We cannot stop. Now, then we have to develop a system to assess the risk so that we can make a better decision. So the environmental risk assessment is actually a tool. Sorry, Professor, would you mind mute your mic? Sorry. Okay, sorry about this. So the ERA is a tool enable us to objectively determine the probability or likelihood that contaminant release or process like hot water discharge, either in the past, current, and future, pose an unacceptable risk to human health or the environment. So based on the result, the decision makers can make informed decision in the risk characterization and the selection of cost-effective remedial cleanup measures. These tools have been widely adopted in various countries, including those in East Asia, in China, and Taiwan, Japan, and South Korea. So these tools give us a very systematic way to evaluate organized data, available information. It also provides some basic assumptions when we run the risk assessment. It also allows us to assess the uncertainties in our prediction. So we can use these tools to cover all kinds of stresses from chemical, physical, and biological stresses, okay? Chemicals, pollutants, physical stresses like hot water or radioactivities. And then for biological, like pathogens, virus, we can also make use of this ERA tool. So before we start the process, we have to define what is acceptable and not acceptable. So we have to define the adversity. It is not straightforward because a stressor may present a negative effect on one ecosystem, but may be good for the another one. For example, if we talk about ammonia as the stressors, it is very toxic to fish, but it is good for plant. If your ecosystem only concerned with plant, then that is good. But if your ecosystem considering all kinds of animals, then ammonia is no good. Then it depends on the situation. Then we have to define the adversity in site-specific manner. Then in general, the unacceptable changes or undesirable changes are those that can alter important structure and function of the ecosystem. Okay, then this is a common definition. If we try to protect the entire ecosystem, then we will look at whether this stressor will affect the ecosystem structure and their function. Okay, for example, providing oxygen for us to breathe, or providing the cleaning by the biowafts that we need for the environment. If those functions being diminished or removed, then we can see this is unacceptable. But very often we will try to look at the biodiversity, say how many species in the system now, and then whether such discharge of pollutants will reduce significant amount of species, leading to unacceptable concern, then we will draw the line there. So during the consideration, we will also take into account of the type, intensity, and scale of the stressor and their effects. And also we will try to look at the potential recovery. If the chemical pollutants will be degraded really shortly, only have a very short-term impact, and then the ecosystem can recover quickly, then the risk we are talking about is lower. Then those chemicals really persist and will have higher chance to be bioaccumulate in the biota, then the risk will be much higher. So all in all, the risk managers or the government must decide what is acceptable, the acceptability of the adverse effects, okay? This will form the basic baseline for the whole risk assessment process. Okay, now, okay. Now, in the process, we will use both qualitative approach and quantitative approach. Qualitative approach, we use a relative measure, high, low, large, and small. And then quantitative approach, we actually need to have data measurement to calculate the probability. So in the process, we have two types. One type is called prospective, the other one is retrospective. For example, for prospective one, maybe a company wants to launch a new chemical product, and then we want to test whether this product is safe to the environment and human health. And then we will judge whether this product can be launched to the market. If there's certain risk of this product, maybe we have to control the volume of production per year so that we will keep the discharge amount below the safety limit, ensure there will be no unacceptable consequence. So we use the result to predict for the future project, future action. If the risk of the chemicals is very high, then we abandon the proposal. We also have the situation that for legacy chemical pollution, we do the retrospective risk assessment. That means the chemical stresses or other stresses already existing in the ecosystem. Then we look backward. Based on all available information, we judge whether there is a causality, the the crisis or the damage of the environment actually linked to the discharge of that stresses. So we do it retrospectively, just like a detective policeman to go to crime case and then collect information to find the causality. Then in reality, both approach can be used at the same time. For example, we use a retrospective risk assessment to evaluate the cause of amphibian decline, okay? Then the result actually can be applied to predict the future of the amphibian population due to a proposal action or proposed stresses to be launched in the market. Then in this case, we have a combination of retrospective and prospective risk assessment together. Now, talk about the process. The process has three main steps: problem formulation, parallel analysis of exposure and effect, and then finally is a risk characterization. You can get a copy of this textbook from US EPA. I will provide you the link at the end of my presentation. So problem formulation, we need to define the problem. Then what kind of stresses we're talking about, what are the receiver, what is the assessment endpoint, that means the unacceptable consequence we looking at. Then from there, we look at the actual or predicted exposure level and also compare the effect level. That means our threshold, effect threshold. Then we do a comparison, then we find out the risk level, and then that will trigger the management decision. So in the first step, during the problem formulation, we ask these questions. What is the stressor? Second one is, what is the sensitive receiver? The third one is, what is the assessment endpoint? What we're going to measure to evaluate the risk? And then how to conduct the entire process. Then we need a conceptual model and planning. So let me show you one example. For example, we're going to spray a new commercial biocide in the farm field using aeroplane like this. Then we have to ask how and what happened if we discharge this biocides in this big area. Then we can look at the food web structure. Very often we say if we can protect the top predator, the population still remain stable. That means the whole food web structure will be protected too. So very often the environmental authority will use the population parameter as the assessment endpoint. Sometimes they may use valuable fish species like salmon. They are sensitive to pollutants to look at the health of the aquatic ecosystem. So then they will use the reproduction parameter of the salmon as the measurement endpoint. So in terms of a conceptual model, then we will look at different pathway of the discharge process, air, soil, water, and then we look at different sensitive receiver, terrestrial vertebrates, terrestrial plant, aquatic invertebrate and vertebrates. And then we also try to work out what we're going to see changes if there is a disaster happen. So for example, we'll look at aquatic animals and plants to look at their survival, growth rate, and reproduction. So this framework have been used for the endosulfan. It's also a biocide in the farming site. So once you have this conceptual model, then we know what to measure. So if we want to look at the impact to the aquatic life, then we need to define the threshold for the survivorship, growth, and reproduction. Then use that as a benchmark, what we find, the concentration, if the chemicals have yet to release into environment, then we use model to work out the hypothetical exposure scenario. Then we compare it with the effect benchmark. We call it predicted no effect concentration. Then the next step is to compare the exposure against the toxic effect. But the process is not straightforward. We can define the toxicity like a effect concentration or lethal concentration. We can gather those data from laboratory. But at the same time, we also need to examine the exposure scenario. Will the chemicals come from the water, come from the food, or come from other land-based discharge? Then how often the organism will expose to such polluted water? Then it becomes all by chances, because different organisms have a different habit. They may not have the same kind of probability to expose to the same chemicals, okay? Even though they live in the same environment. So we have the probability, even for the same species of fish, some fish may be more susceptible to the toxicant, some don't. Some fish may prefer to hide away from pollutants, then they are cleaner than those fish doesn't care about the pollution level. Then you will create different probability of the encountering between these two parameters, toxicity and exposure. Let me show you one just example or analogy, okay? So if I'm talking about this Malachi green, it's a fungicide, heavily used in fish farming in some region to protect the eyes of the fish won't become white in color, and also to protect them from secondary infections during the transportation. I think someone joined on the pot. I don't know whether I can clean it. It's okay now. So back to here. Then if I ask question whether it is safe for me to eat this fish with Malachi green inside, then I just ask question if the level in the fish is lower than the recommended safe level, then I'm okay. So I can eat little bit of this chemical without too much harmful effects to me, okay? So, I don't know why I cannot go to next, okay, now, okay. Now, this is we call it, just now we call it lung cancer risk. We actually compare the intake levels against the reference dose in the fish, okay? If the intake lower than the reference dose, I'm safe. If higher, that means I shouldn't do it. Maybe we should stop selling the fish. Another factor is called cancer risk. The calculation using this equation, the amount of intake multiply this cancer slope factor. Normally, in normal situation, this is 10 to minus 6, okay? That means 1 in 1 million will have a chance to have cancer without taking any pollutants, okay? Then for those carcinogen or co-carcinogen, then this slope will go down to say 10 to minus 5 or, I'm sorry, 10 to minus 5 or even 10 to minus 3. So that means the chance of having cancer will be increased for those carcinogen compounds. Okay, so by combining these two analyses, then we will know the risk level to me if I consume this fish. However, in the environment, we have many different species, not just one type of species, just human. In a marine system, very often we have over hundreds, even thousands species in the system. Then each species will have different response to the pollutants. That is the green distribution here. The orange distribution means the environmental concentration in the region. Some region closest to the river mouth, the discharge point, you're going to have a high concentration. But the area closer to the open ocean, then you will have lower pollution level. Then we have a barrel shape, very often we can see. Then we compare actually between the exposure against the effects. We compare two different distributions here. If they overlap, that means in certain case, they're risk over 1 by means of the ratio between the PEC and PNEC, the environmental concentration against the threshold. If they only touch a little bit, that means the risk is not too high. If they separate like this, that means no problem at all. So then we use the available information, we can judge the risk level of the stresses. We can apply this technology or approach in the oil drilling platform in Norway. We can have real-time risk map. Then we can see when the risk quotient is higher than 1 is red in color, and then intermediate yellow color. Then we know the risk in which area suffer more. Then we can implement different management measures. Finally, the process is that once we have the risk characterization result, then the risk manager can make the following 3 decisions. 1, the chemicals or the stresses is safe, we can go ahead with the proposal and the project. In the second situation, the risk is very high of the chemicals of the stresses. We have to abandon the project, okay? Stop there. But very often we have the third scenario. There is some risk of the stresses, but it will give us benefit. Then we have to judge risks and benefits again. Then in that situation, we have to minimize the risk by restricting the discharge and also put some measures to control the discharge so that the levels in the environment remain acceptable. Then we have to use risk management in this scenario. However, the concept of risk is very different among different people. So then the risk communication is very important. Even though we have scientific evidence saying that the risk is low, then you may find some chemicals inside the fish, say the mercury, the regulatory limit is 0.5 milligram per kilogram. So if we find 0.001 milligram per kilogram mercury in fish, okay? For some people, they say this is not acceptable, still have mercury, very dangerous for consumption. Then they may say that ignore our risk assessment and then ask everyone don't eat fish. And that will affect the fisherman and also the fishmonger who's selling the fish. They will suffer because people run away not eating the fish anymore. So once we have the result, we have to tell the people with scientific evidence and then tell them what to do. In fact, they can eat the fish. Maybe some species of fish will have higher concentration, like those tuna. Then they should have less consumption, moderate consumption. We have to tell them how to behave so that they can minimize the risk of exposure. Then in the next lecture, I'm going to tell you more about the risk communication. Okay, so to end my lecture, I want to show you this video. Okay, it's a summary of what I said just now. Again, so let me remove that drawing first. Okay. Now, I hope you can you hear the sound? Grace, can you hear?
Hi there. Okay. My name is Jan, and I work at the European Food Safety Authority, EFSA, where I'm involved in the environmental risk assessment of genetically modified plants. Today, I will briefly explain you.
Oh, sorry, I make a mistake. Okay.
Hi there. My name is Jan, and I work at the European Food Safety Authority, EFSA, where I'm involved in the environmental risk assessment of genetically modified plants. Today, I will briefly explain you what we mean by environmental risk assessment and why it's so important. The environment is a broad concept that describes our biophysical surroundings. It includes air, water, land, and living organisms such as plant and wildlife. Environmental risk assessment is a scientific process that identifies and evaluates threats to the environment, in particular to living organisms, their habitats, and ecosystems. The causes of environmental threats are diverse.
Oh, sorry. I cannot click. Sorry. I shouldn't click on those.
So important. I will briefly explain you what we mean by environmental risk assessment and why it's so important. The environment is a broad concept that describes our biophysical surroundings. It includes air, water, land, and living organisms such as plant and wildlife. Environmental risk assessment is a scientific process that identifies and evaluates threats to the environment, in particular to living organisms, habitats, and ecosystems. The causes of environmental threats are diverse. Some are largely natural, for example, earthquakes or volcanic eruptions, whilst others might be the result of human activity, such as industrialization and urbanization. Think, for instance, about air pollution, toxic chemicals in food and water, poor housing, and sanitation. In the European food safety system, EFSA is responsible for carrying out risk assessment of products which may have a direct or indirect impact on food and feed safety. Because the use of these products may pose risks to the environment, EFSA also considers these environmental risks in its assessment. EFSA performs environmental risk assessment in a number of areas, such as genetically modified organisms, pesticides, plant pests, invasive plant species, and feed additives. The purpose of these assessments is to assess the seriousness and the likelihood of harm to the environment which might arise following a specific activity, such as the cultivation of a particular GM plant or the application of pesticides. These assessments follow several stages, beginning with problem formulation. Problem formulation is the first critical step because it defines the scope of the environmental risk assessment by specifying what needs to be protected from harm and by identifying potential harmful effects. Problem formulation is then followed by a hazard and an exposure characterization. In the hazard characterization, potential hazards and the seriousness of potential harm are examined, whilst the exposure characterization considers the likelihood and the level of exposure to the hazard, and thus how likely it is that harm will occur. The final step involves the characterization of risk. Here, the seriousness and the likelihood of harm are combined to estimate the level of risk. In some cases, the environmental risk assessment also includes risk mitigation measures. Such measures aim to reduce an identified risk to an acceptable level or a level of no concern. The environmental risk assessments carried out by EFSA help risk managers and policymakers at the European and national level to ensure that products that are put on the market do not cause unacceptable harm to the environment. Thank you for your attention.
Okay, great. We have to. So these are the link. You can download the reference I just used as a teaching material. And also there is a training website in the US EPA. You can go through the details step by step. So maybe I stop here, then we can have some discussion. I see how many of you have questions. Any questions? You can drop questions in the chat room as well. So, Jining, how much time I have for my second talk?
Oh, so you still have 9 minutes.
9 minutes.
Yeah. So we have plenty of time for discussion. Yeah.
Okay, then
so we open this for the floor. Yeah, for the audience.
So move on to next talk. Then, if no one asks questions, because I still have one more PowerPoint on the.
Oh, okay. All right. Yeah, please go ahead.
Okay. Oh, sorry. I still have. Let me see. I need to open that file first. Okay. Okay. Can you see the screen? I'm sorry, I've been overrun for the first talk, and then I will cut short of my second presentation.
Yeah. Professor Lau, we do have a question from a participant in the chat box. So Hildy asked, would standards for environmental quality be similar across the region? Thank you, Hildy.
Okay, that's a good question. The answer is yes or no, because we find that there are some regional differences of the chemical behavior because of different temperature. And also we find that different species composition in different regions also causing different response. So by and large, what we find is that tropical region and temperate region, cold water region should have different standards, okay? But for, say, for all tropical region in East Asia, I believe we can use one standard in the region. We can develop a set of standards for the region that is acceptable. That means those criteria established in Hong Kong, Malaysia, Singapore should be quite relevant and can be used together. So the second question is, there is an allowable level, a substance in food like fish. How do we treat fat-soluble substance that can be biomagnified? That is also very good questions. In the very detailed risk assessment, we're not just looking at toxicity itself, but we also look at the bioaccumulative potential as well as carcinogenic potential. So then if the chemicals has a high tendency for biomagnification or bioaccumulation, then during the development of the criteria, that means the predicted no effect concentration, we will make use of a safety factor to make this PNEC level even lower. Okay, if they have high tendency, really persistent and bioaccumulate and biomagnify in the ecosystem, even though say the original PNEC is a 10 microgram per liter, now we have to divide it by an additional factor of 10. Then we tighten the criteria to 1 only. The original 10 now divided by 10, then it become 1. So then it depends on the intensity of the biomagnification. Then we will include a factor to encompass such impact. Okay, so then that means when we use that modified PNEC, already include a decision on the biomagnification issue. So I think this is a really good question. We must have a separate lecture just talking about how to develop a water quality criteria, food safety limit. We will be happy to do so in the future training workshop. I think this is a very good question. Okay, now let me move back to the risk communication. I will try to convince you risk communication is important through a lesson, a case study. Today, I won't have time to go through all the details, but I will share this PowerPoint with you, then you can read it. Now, let me start. Okay, so after doing the risk assessment process, we also have to do risk communication and risk management. Why this is important? I'll give you an example about biocide, DDT in seafood study. The people's perception is very different from the actual hazard, and also very often there's a rumor, there's a pest, the social media, they may give wrong impression to people, say that all this mixed together, the perceptional risk is different from what we find from our scientific study. So there is fundamental saying that the risks that scare people and the risks that kill people are very different. But people often mix these two up, okay? And in the society, there are very diverse views on different environmental issues, food safety issues, because different stakeholders, they hold different agendas. For example, the NGO always want to have clean water, clean food, and push the government to do more. Then if just little bit of mercury being found in fish, they will say this will kill people. Then that will affect how citizens respond to the crisis. So very often such environmental crisis would lead to fear-driven, damaging public responses. So I give you one example. This was the newspaper in Hong Kong talking about the DDT levels in 70% of marine fish exceed the safety limit. And then you know what, after this newspaper came out, then the following days and weeks, no one buy fish to eat. So then the fishermen and also the fishmongers suffer a lot. But in actual fact, you still have other fish to eat. You have freshwater fish to eat. You still have 30% of fish without DDT. So then sometime in this crisis situation, if we cannot diffuse or channel our correct message to this society, that will create this unwanted response. So that's why risk communication is essential, because now we have the scientific evidence and then know what to do to minimize the risk. We have to share this information to citizens. So the risk communication is a two-way process, interactive process to exchange information with various stakeholders and the general public. And then at the same time, we try to ease the public concern, say the risk is low, and also there are alternative choice of fish to eat. And then we also tell them that those tainted or problematic fish, we will remove, and then we will ensure the confidence of the consumer, and then try to protect the fishermen and also the fish seller business. So we also need to well structure our message in different media, okay? For example, 30-second sound bites for TV news, 30 minutes in press conference. We also need to prepare different graphics and also the press release the key message to all the reporters. So we have some purpose for the risk communication. First, easy public concern, okay? Guide them how to respond, how to minimize the risk exposure, and try to listen to them and then understand their concern and then try to address their concern. Finally, we also explain the science and the nature of the risk assessment and the risk itself. And also we'll clearly tell the people that there's some uncertainty in the analysis. We will gather more information and then we'll update the people from time to time. So try to end this lecture with a real case study so that you know what I'm talking about. He was the food safety controller in Hong Kong, but now he retired already. When he started his job, then he has not much experience in risk communication. Then a piece here, what he said. I need to. I think maybe.
The biggest problem that we are concerned with is its effect on developing brain. That means the brain of developing fetus. A woman needs to take only 2 to 10 slices of sashimi. And if that kind of sashimi come from predatory fish with high level of mercury, that level may be excessive. All the fish that we have examined contain mercury at different level. And majority, over 95% of the fish contain a low level of mercury. So it's safe to consume fish. But a small proportion of fish contain high level of mercury, and some exceeded our regulatory limit of 500 microgram per kilogram.
So after hearing this, I would like to ask you whether you think you feel safe to eat fish. I think you may share with my feeling that it's not safe because the way he talking about the embryo brain development and then he said he didn't say pregnant woman. I assume he's talking about pregnant woman. Just take 1 to 2 to 10 slices of sashimi, assuming it will affect the fetus brain development, okay? Then I have a question because in any sashimi restaurant, the size of the slice will be different. In Hong Kong, in some sashimi restaurant actually have a very large slice. This is not really good for risk communication. It's better you using standard unit, like how many grams you eat, rather than using this jargon slide. And what kind of predatory fish he didn't mention. And then he said that level may be exceed. What level, we don't know. And then most strikingly, he said something that all fish that we have examined contain mercury. That gives people the impression that all fish are not good to eat. Then he suddenly say, over 95% of them contain low level of mercury. How low? Then what is the definition of 95%? We should try to avoid using percentage in our communication. For example, if the government actually measured 2,000 fish, and then only 5% of them having an acceptable level of mercury, and then those samples including just 2 species, one is tuna fish, the other one is big eye, then citizens should avoid to select these two species. Then people know what to do. You need to guide the correct behavior rather than sidetrack people, give this wrong message, then create unwanted response from the citizen. So this is a very good example case to tell you that we have to prepare our speech to the press in a very clear manner so that we can get the correct message across. So in the sense that we need to tell people what is the risk we're talking about, what are the fish with problem, people can have choices, and then how to minimize the risk. We also need to tell those sensitive groups like pregnant women, children, they must avoid consuming such kind of fish product. So this is a very good lesson for us to learn. Then in the process, I try to skip some slide because of the time. The idea is we should have a regular briefing with a centralized body, always the same people or same group of people disclose the latest result, because this risk assessment process should be a continuous process. Then we should provide accurate information. If we don't have the data, we just tell people that we will follow up, just tell the truth. Then there are 7 rules. Plan carefully, evaluate the success of our communication effort. We keep evaluating, improving. Coordinate and collaborate with credible sources like professors in toxicology and food safety, and also medical doctors. Accept and involve the public as our partner. We work together, we listen to them and clear their concern. Listen to them, okay? Be honest, frank, and open. Never say no comment, because no comment has a hidden agenda, and then you will reduce the trust between the citizen and the authority. Speak clearly with compassion, meet the needs of the media and the society. So give you another example. After many years later, then I think the government have been improving a lot. Then this is a good one, and you can see.
The Center for Food Safety released its report on the first Hong Kong total diet study. It found Hong Kong people are unlikely to have major undesirable health effects from dioxins in food, though long-term exposure could cause cancer. The findings showed seafood, eggs, fats and oils, and meat contain dioxins. The 3 food items with the highest levels of dioxins are seafoods, mandarin fish, oysters, and pomfret fish. However, Center for Food Safety consultant Dr. Ho Yuk-in said people should not panic about eating fish, saying moderate consumption of a variety of seafood should not cause excessive exposure to dioxin. He also advised people trim fat from meat and consume low-fat dairy products to reduce dioxin intake.
So this is a good example because yes, I want to go back to one slide. Let me find that. Sorry about this. Yes, the communication goal is that we need to ease public concern. Just tell people that the general risk is low. You have other choices of food. We just need to avoid those items, guide their behavior. That's very, very important. So I think at the end, through the learning curve, then the Center for Food Safety improved a lot over the years. Now the communication is much effective. So maybe I stop here, given the time, and then I can handle some questions from the student, from the audience.
Okay, thank you very much for Professor Leon's and vivid examples and personal reflection in terms of environmental risk assessment or communication management, which makes the complex process quite clear, okay, or simple. And so there's a question, okay, from Razon Brando from University of Philippines, okay. So he asked about, in ERA, there is an allowable level of that can be biomagnified. Yeah,
I think I answered that one already. Just
yeah, already answered.
Yeah.
Sorry. Okay. So then, any other questions? Any other questions from the audience, please?
Yeah.
All right. Otherwise, we will have just because we have a little bit overrun. Maybe we take a 5-minute break. We shorten it and return to the platform on 35. Okay, of 10:35. Yeah. Thanks, Tay.
Okay. Thank you very much.
Thank you very much. Welcome back. And so then let's move to the next speaker, Dr. James Fong. He is an assistant professor in Department of Applied Biology and Chemical Technology, the Hong Kong Polytechnic University. His main research area includes marine biology, environmental toxicology, cellular biology, ecophysiology, and analytic chemistry. Okay, also, again, a very wide range of spanning from chemistry to biology to toxicology. So today he will provide a training on under the topic of microplastics pollution. Yeah, please, Dr. Fong.
Yeah, good morning. Can you see my square screen, please?
Yes, it's very clear.
Okay. I may have some technical issue here, but it should be fine if you can see my screen. Let's start. Yeah. Good morning. This is James from Hong Kong. Since this is a technical workshop, today I will focus on methodology when we talk about microplastic pollution. I believe all of you should have some basic background in microplastic. Therefore, I would like to skip the introduction. We directly jump to the methodology, how we develop a method to analyze microplastic in biological sample. Here we will use the Raman spectrometry to identify microplastic in seafood and other biological samples. This slide shows you the common procedure of what we determine microplastic in biological or environmental samples. Each procedure comes with its own technical concern. Here they are. In this study, we try to address this technical concern one by one. Objective 1 is to identify a suitable substrate. As you know, microplastic are solid particles. We have to use some filter membrane or sieve to isolate these particles from liquid media in order to facilitate the next step. We use different type of filter paper. However, the material of this filter paper will cause some interference to some specific spectroscopic approaches, for example, Raman spectrometry. Therefore, we like to compare the performance of different filter paper and to identify the most suitable one. When we have to extract microplastic from biological sample, we want to digest the biomass, organic or inorganic biomass, as much as possible. Some of this digestion method may not be complete. They may not be complete. Therefore, in some cases, we lead the next step, density separation. The undigested biological materials together with microplastic will be placed in a high density solution in order to float the lighter microplastic to the surface for easier collection. This is the density separation step. Incomplete digestion will cause some problem. For example, in Raman spectrometry, as you know, biological materials, a lot of them have octofluorescence. This octofluorescence is the major interference to Raman signal in the analysis. About density separation, it works for most type of microplastic. However, based on density separation, it is less effective for some higher density microplastic. Therefore, we may lose part of the microplastic of concern. In this study, objective 2, we try to increase the biomass digestion efficiency of our digestion process in order to bypass the need of density separation. This is objective 2. When we have isolate microplastic, we will use Raman spectrometry to analyze, to identify what they are. However, the chemicals used in this treatment, the treatment I mean is the biomass digestion treatment and the density separation treatment, they may cause some damage. Or sample loss to the particle themselves, Therefore, we would like to determine the particle recovery rate of microplastic under the digestion method that we developed in objective 2. This is objective 3, the particle recovery rate. The next objective is to assess any change in morphology or surface damage of this particle due to the use of different chemicals in our method. Okay, objective 4. Objective 1, 2, 3, 4 will allow us to develop a method, to develop an improved method compared to the common approaches. Then we come to objective 5. We try to identify microplastic using a more advanced approach, automate mapping approach. Why do we do this? Because the conventional approach to identify particle one by one is time consuming and prone to handling errors. Therefore, we use the Raman technology to develop an automate approach to increase the efficiency. Okay, this is the overview of this lecture today. How do we develop a method that can improve the current approaches in microplastic analysis? Objective 1. The first objective is to identify a suitable filter membrane to isolate microplastic from liquid media. Here, we compare 3 types of common filter paper made of glass fiber, cellulose ester, and stainless steel. In this graph, I show you the Raman signal of each materials. Look at the glass fiber. It has a strong fluorescent peak that is not appropriate, which cover most of the signal of the plastic polymer, which is not good. Cellulose ester contain a lot of carbon, hydrogen, and oxygen, and this composition indicates in this peak in its Raman spectrum, which is not ideal too, because a lot of this peak overlap with the peak of plastic polymer. Now we look at the stainless steel membrane. It has low signal level with flat baseline, which seems to be good, From this data, we think stainless steel may be good. So the next step, we do an evaluation. We put polystyrene, PS, a common type of microplastic with different particle size, 10 micron, 100 micron, 300 micron on each type of this filter paper: glass fiber, cellulose, and stainless steel. We found that for the larger particle size, larger than 100 micron, the effect of filter paper seems to be okay. All type of filter paper are doing well in this particle identification under Raman spectrometry. However, when the particle size reduced to around 10 micron, the glass fiber and cellular ester, they just don't work. They just don't work. If we look at the peak of the polystyrene on these two types of materials, very clearly, the characteristic of polystyrene disappear when the particle size decreases to 10 micron. The shape just totally different with what we expect from polystyrene. Look like this spectrum and that spectrum. However, stainless steel, even the measuring index, the efficiency to identify the material decreased to around 0.5. The peak and the characteristic of this Raman spectrum can still be distinguished, can still be identified. Therefore, from this data, we conclude stainless steel membrane is among the most appropriate compared to the other two materials in Raman spectrometry to identify microplastic. Good, now we have identified suitable materials for membrane filter. The next objective is to increase the biomass digestion efficiency. When we have the biological sample, we want to digest the biomass to extract the microplastic. Here we use two types of biomass as demonstration: mussels and fish, mussel and fish. We have three types of treatment: K, KH, and KHE. K represents the treatment of potassium hydroxide. KH is the treatment of potassium hydroxide added with hydrogen peroxide to boost the digestion efficiency. KHE, the condition is very similar to the condition of KH, but we add EDTA, a common decalcifying agent used in histology. Okay, we use EDTA here to digest the calcium-rich tissue type. For example, the mantle in mussels and some bone fragment in fish. In total, there are 6 treatments. Mussel free treatment, fish free treatment here, in total 6. Here, result. We look at the mussel biomass. All 3 types of treatments, they did well to digest the biomass of mussel. The digestion efficiency higher than 99.9% in terms of weight, in terms of dry weight. When we look at the fish biomass, the digestion efficiency is much improved when we have added EDTA in the KHE treatment. Okay, increased by more than 20%. Now we look at the photo of the filter membrane, showing you the amount of biological residue after each digestion treatment. For mussel, in the treatment K and treatment KH, the conventional digestion method, there was still a lot of biomass remain on the filter membrane. They are very lightweight, and therefore they cannot be really represented by this data using dry weight, because they're very light. They are light, but they cover a large area on this filter membrane. As we have discussed on the last slide, these biological materials, they have a strong octofluorescence that can interfere the Raman signal, which is not good. And therefore, for mussel, we recommend KHE, the treatment KHE. You see the digestion is very clear. For fish, the result is even clearer. The biological residue here, mostly bone fragments. The efficiency is impressive for fish. Good, good, good. From this result, we have identified the treatment KHE is more suitable for the digestion process for fish and mussel in comparison to the conventional digestion method. What's next? The next objective is to determine the particle recovery rate using the KHE treatment. What do we do here? We have 3 treatments of KHE, chemicals only, and the treatments, the KHE solution with the mussel biomass and with the fish biomass. 3 treatments. We use 7 types of microplastic in this evaluation. We mix all this plastic together and split into the 3 treatments, which were subject to the same digestion procedure. After the digestion, we retrieve this plastic particle on stainless steel filter membrane and to identify and locate this particle on this filter membrane using Raman spectrometry. The results are shown in panel B and C and color code. We can identify different types of microplastic, where are they on the filter membrane. Good, impressive finding. The recovery rate, here are the data. The results are impressive. The recovery rate, we can achieve 90 to 100%, which is good. Now we know our method can have a high recovery rate of microplastic. The next question is, if the use of this chemical will cause any damage on a particle, because Raman spectrometry or FTIR, the infrared approach, mostly concerned on the surface characteristic, the surface composition of different chemicals, different compounds, I mean. If there is any damage or change on the surface, the result may be affected too. Therefore, we'd like to see any change in size, any surface damage, or any change in morphology on the surface of microplastic. Here are the results. On this slide, we compare the surface of microplastic not treated with KHE and treated with KHE. They are different particles. Some particles treat with KHE, some particles don't. We didn't observe a clear change due to the KHE treatment based on scanning electronic microscope. This is the SEM images. We don't observe any clear change. Then we use another approach. We use 3D scanning technology, 3D laser scanning technology. We scan the surface of particle to see the change in surface area. Again, the surface area remains very similar before and after the treatment KHE. Some slight change were detected on polypropylene and PVC. They are tested by dependent t-test, therefore even the error bar is large, you still see the difference. But still, even we detect this minor change, does it affect the accuracy of our approach? Does this affect the accuracy of Raman identification? This is the important question. We know any chemical will induce a certain extent of damage on the surface of particle. But does it matter? Does it matter? This is the question we want to find it out. To answer this question, we compare the Raman spectrum before and after for 7 types of microplastic, same as those used for the recovery test. Epoxy pudding is not relevant here. You can ignore this graph. 7 types of microplastic, yes, the red color represents the Raman spectrum before KHE. The blue color represents the Raman spectrum after the treatment KHE. They look very similar, but how similar? We try to correlate the spectra before and after, and we found that they are highly similar. They are highly similar. 94 to 99% similarity. Okay, this finding tell us, okay, the method is good. Even we use some chemical and this chemical induce minor effect on the surface, the identification can still be efficient, up to 99%. Good. From the finding from objective 1 to objective 4, we have developed a method to identify, to extract and identify microplastic from biological sample. In this case, seafood sample. The last objective here is to develop an automate mapping approach for microplastic to improve the conventional approach, which is more time consuming and prone to handling errors. On this slide, I show you 2 particles, polypropylene and polyethylene. Here I show you the Raman spectra of them. The red color spectrum is the sample spectrum. How do we do the identification? When we get the red color spectrum, sample spectrum, we match this spectrum to the database that we have to match this spectrum with a lot of plastic standard spectra to identify what it is. For these 2 particles, they were identified as polypropylene and polyethylene. You see the peak position, they merge, they are matched perfectly. Okay, high identification. This is a single particle approach, We want to improve this single particle approach to a higher throughput. How to do multiple identification at the same time, over the same period of time. This is the example. Let's say we want to identify the particle in this 2-dimensional area. We get the Raman spectrum at each single cross point on this grid. If the particle fall on this cross point, they can be identified. In this example, the 4 red color particle can be identified. However, if the particle is too small, if the particle is smaller than the interval between 2 cross points, they cannot be identified because they are too small. Therefore, the interval between the 2 cross points also defines the resolution of your spectroscopic approach, which defines how small the particles we can detect in our method. Using this concept, we have developed a method to identify particles on stainless steel membrane. This is one of the results. In panel A, I show you the stainless steel membrane. On this membrane, you see some patches of biological residue, also microplastic. Panel B show you the automate mapping approach using Raman spectrometry. In this case, we can identify 3 types of plastic polymer, polypropylene, polyethylene, and PET fiber, the PET fiber here, which is common in marine environment. Panel C is the superimposed image of A and B. From panel C, we can locate where these microplastics are on this film membrane. Okay, this approach is good and reliable and save much of our time because it is automate. Using the method developed on the last few slides, this is the result from mussel and fish collected from Hong Kong. When we do the analysis of microplastic, we usually report the number, the quantity of microplastic in this individual or per unit weight, per unit dry weight or per unit wet weight. In this case, per individual. We have the size distribution curve for fish, for mussel and for fish. We also report the shape of this microplastic. In this case, we only find fragment and fiber. The most important data is here, the polymer type, the polymer type. In this case, we identified that polypropylene is the dominant type. Okay. When we report microplastic, we usually report these three parameters: the quantity, the shape, and the polymer type. This slide summarizes what we have discussed on the last few slides. When we have the biological sample, we use the treatment KHE to digest the biomass, then to extract the microplastic retained on stainless steel film membrane. The particles, including microplastic on this stainless steel membrane, are identified by an automated mapping approach of Raman spectrometry. This is the flow of the analysis of microplastic in our lab. Now we have the method. The next question is, we know microplastic exists in seafood, for example, mussel. We would like to know then how many pieces of microplastic can be ingested by us, the human. We have done this study in the eastern water of Hong Kong at 5 important mariculture zones in Hong Kong. We collect mussel, analyze the microplastic, and to estimate the human ingestion rate through consumption of this bivalve shellfish. Here the result using the method I've shown you on the last few slides. From north to south, we quantified the number of microplastic in this mussel. We have identified the high-risk area among different locations. In this case, in Tolo Harbor, the Yin Bay area with slow flow. On this slide, this is the mapping approach that we have just learned. From this study, we have done a more careful size distribution curve to show you the particle size around 100 micron is the most abundant in the Hong Kong waters. On this slide, I show you the Raman spectrum of polypropylene isolated from the mussel sample collected from Hong Kong water. 3 pieces here. Polypropylene represent the most abundant polymer type in mussels in Hong Kong. As we have discussed, when we report the data, we report the polymer type, we report the shape, and we report the shape in terms of each polymer type. Okay, something interesting we found here, a lot of this microplastic in fragment form. However, PET, they mostly occur in fiber. Now we come to the most important question. How many pieces of microplastic can be ingested by us through mussel consumption? In order to estimate the human consumption rate, we need the data from another source. We need the consumption rate of bivalve shellfish before we can calculate the injection rate of microplastic through mussel consumption. Okay, the consumption rate of bivalve shellfish and other seafood, the data provided by the Food and Environmental Hygiene Department based on Hong Kong population. We have this piece of information. Here's the data. The whole population average is around 800 grams per person per year. Within this whole population, 15 of them are regular consumer of seafood. They have a higher consumption rate of bivalve shellfish, around 5,600 grams per person per year. With this data and with the data of microplastic we collect from our study, with this and that, we can calculate the human ingestion rate of microplastic through consumption of mussel. Here the data, simple calculation, multiplied by this and that. Now we have the number of human ingestion rate. Is this number high or low compared to other places? Then we have done a comparison worldwide. I have highlighted the data in this study from Hong Kong. This column, the third column, show you the human consumption rate of bivalve. The next column show you the human injection rate of microplastic calculated from the consumption rate of bivalve. Okay. When we compare this column, it seems that the human injection rate of microplastic is quite high. Similar to this value obtained from Europe, and our values are higher than all other previous study. Okay. Conclusion here is the human injection rate of microplastic is high in Hong Kong, and probably some other region in Southeast Asia too, because we have similar eating habit and diet. The data can also be expressed per meal. How many pieces of microplastic can be consumed in a single meal if we consume bivalve shellfish? Again, I highlight our data here, up to 458. This number is higher than some other study, but much lower than this study in Italy. Okay. In conclusion here, the ingestion rate of microplastic in Hong Kong and some other places worldwide are high. Now we know we ingest a lot of microplastic every year, but so what? What does it mean? Are they harmful? Do they cause any harmful effect on us? This question is important, but remain unclear. We need more research, including research in my lab. We are trying to estimate the human health risk of microplastic. But at least we know we are eating a lot of microplastic every year. Apart from mussel, now we move to oyster. Why we move to oyster? Because oyster represent a more popular seafood worldwide. How do we eat oyster? A lot of us eat oyster raw without cooking, which induce even higher risk of contamination. What we have been doing, we have been collecting oyster in the East Asia region, including China, Korea, and Japan. We have been doing this since 2019, and we collect oyster sample every year, try to find the temporal pattern, spatial temporal pattern of microplastic in the East Asian region. Our next step is to extend our study to the Southeast Asia region. We have contact collaborator in different countries. They have agreed to sample oyster for us. However, under the situation of COVID-19, our sampling has been postponed to next year. It was supposed to start in this year, but unfortunately, because of a lockdown, we just couldn't get the oyster. So we start from next year. If you are interested in this collaboration, you please feel free to talk to us. We are happy to collaborate. This is part of the project of Professor Kenneth Leung, the Worldwide X-ray Project. It's part of his project. That's the end of my presentation today. In this, if you want to know more information about what we have discussed, please read these two papers from my lab. Okay, this study is supported by the State Laboratory of Marine Pollution at the City University of Hong Kong. Thank you. Now we come to Q&A.
Yeah, thanks, Dr. James. So very interested and very interesting plastic story. And also think about the risk. Okay. Right. So to save time, maybe we can only accommodate one question from the audience. Any question from the audience? Please, either you type in the chat room or just speak it out. All right, or otherwise we will move on to the next speaker, okay, Professor Rudolph Wu. So Professor Rudolph Wu is a professor and advisor in environmental science from Department of Science and Environmental Studies, the Education University of Hong Kong. His main research area includes environmental science and management, and marine ecology, marine pollution, and ecotoxicology. Today, he will provide a training under the topic of environmental monitoring. Yeah, Professor Wu.
Yeah. Good morning, everybody. And James, could you?
Sorry, how can I unshare? Stop share. Okay, I found it. Okay, thank you.
Hold on. Yeah, can you see the slide? Can you
not really.
Slides, guys? Not really.
James, please quit rather than stop sharing.
Chris, oh, okay, let's see.
Can you see the slide now?
It's clear now. Thanks.
Okay.
So please go ahead.
Okay, good. Thank you, everybody. And today I'd like to talk about environmental monitoring. As everybody working in the environmental field will know, that the vast majority of work and research are dedicated to environmental monitoring and environmental control in order to let us have a good and healthy environment. Now, and in this talk, I'll talk about environmental monitoring. Why bother? Why bother spending so much money in doing environmental monitoring? And there's two major types of environmental monitoring. The first type is physical monitoring and chemical monitoring, which is relatively easy. And the second part is still in the developmental stage, which we call biological monitoring, and which can overcome a lot of shortcomings and which cannot be done by the physical and chemical monitoring. And in biological monitoring, we have two major types of monitoring too. The first is bioindicator, and the second is biomarkers. And I'll talk about these two in great detail in the coming 60 minutes. Now, The first is that environmental monitoring. Why bother? And you see that in every country, every regulatory authority, they try to monitor environmental parameter in a regular basis for long term. Now, the reason is that why bother is that we want to detect these temporal changes of environmental factors due to this pollution. And to ask the question, is that our environmental condition getting better or getting worse, right? So if getting better, so we're happy. Getting worse, we got to do something about it. And the second objective is try to detect the spatial changes of these environmental factors or pollution. So this would help us to identify where's the hot spots, who discharge the pollutant, and to what extent, and where is the most important or most polluted area. And then we try to identify the pollution sources, and then also the area effect, how big an area is being affected. So this will help the environmental managers to make this informed decision. The third objective is try to check the compliances with the established environmental guidelines, air quality objective or water quality objective. Say, in most, if not all government, we have established a range of environmental guidelines saying that, oh, in this area, we should like to keep the environmental variable below this range. And then the air quality, PM 2.5 should not exceed certain limit. Water quality objective, something like the nutrients standard should not exceed this limit. Dioxin should not exceed this limit. And then metals should not exceed this limit, and so on and so forth. And this is why we have to regularly monitor to see whether we are doing a good job or doing a satisfactory job to keep what we promise to the general public in order to protect our environment. And notably, and one question that we asked during Kenny's talk is that for this environmental guideline, air quality objective, water quality objective, they are very different between countries. And there's one country may use a loose system, the other country use a stringent system. It all depends on the number of factors, whether you can afford to do that and whether it's doable. Now, finally, the objective of doing environmental monitoring is to determine whether the environmental level of contaminant is acceptable to the general public and environmental health. Now, just like if we find the mercury level in the environment is higher than what we set, so we have to trigger the government need to do something. Either you tell people don't get the fish, or alternatively, you said, okay, let's control the source, control the amount of pollutant going into the water, and then to protect the general public health. To start with, a lot of environmental monitoring, there's all over the world, they spend lots of money in doing the environmental monitoring. And after a while, they say, oh, we can't afford it. Or we do it for something like half a year, 1 year, and we stop. I'll tell you for nothing. If you either you decide to have environmental monitoring or you don't. And then if you decided to do environmental monitoring, you have to do it on a fairly long term to provide the data so that they can answer your question, just like these two couples. They must have a major commitment saying that, okay, we are going to do this in the long run. Otherwise, just imagine, if you want to sort of detect the level of environmental changes, and then so half a year, 1 year may not give you the reliable data. And you spend lots of money, lots of time in investing into the startup and end up with nothing. Now, first we talk about the physical and chemical monitoring. It's become relatively easy nowadays, and then everybody can spend something like $600 or $500 to buy a sort of a meter, which enable you to measure salinity, temperature, dissolved oxygen all in one go. All you need to do is to dip this in the water, and then they give you the reading, relatively easy. And then, of course, for air pollution, and then you have this station collecting the matters particulate from the air. Now and then you analyze data and so on. And in open ocean or something like in the coastal water, and then you may like to, sometimes you may like to collect seawater or collect fresh water using the water sampler. And afterwards, you concentrate this, and then you do the chemical analysis in your laboratory. But with the advancement of this instrument, and now we are able to do ocean buoy. So effectively, ocean buoy is a buoy, and then you then install the sort of sensor, something like nutrient sensor, dissolved oxygen sensor, or salinity sensor, temperature sensor, or even measure chlorophyll using all these devices. Then you don't have to go and collect the data. The signal received by this sensor can be relayed to the satellite, and then the satellite can be sort of relay the message and the data to your laboratory. So all you need to do is to deploy this buoy, and then you sit in the office drinking coffee, and then you record your data in the logger. Relatively easy, right? Simple. Or alternatively, you can put the ocean buoy down there, down in the bottom of the sea, even deep sea, and then you transmit the signal through either cable or this into the ocean buoy, and then again send the signal back to your laboratory for analysis. So this makes life easier. Now, if you are not satisfied, nowadays, the science advancement can enable us just to measure some of the parameters by satellite. All you need to do, because you know the satellite go around the world either once or twice every day. So from the satellite, you can sense the temperature based on the radiations emitted from the sea. After this, receiving this radiation, you can plot the graph and then plot the picture to tell you what's the temperature in the water all over the world within a very short time. And then we can also extend this to salinity, and based on the relationship between the salinity and the L-band microwave frequency emitted, again, with the satellite, you can collect the data of the L-band microwave, and then you can back calculate the salinity just like this figure, and then so you can again sit in your office and do nothing and collect all this data very quickly. And similarly for chlorophyll, which reflect the total biomass of zooplankton, and then you have this different spectrum of chlorophyll A, B, and C. And then sometimes you can also measure red tide and use this spectral reflectance signature of color and brightness. Again, within a very short period of time, you can monitor these environmental changes in chlorophyll A and to estimate the phytoplankton biomass within a very short period of time over a very large area. So you all think that's very good. Huh? You set up the sensor, set the buoy, and use the remote sensing, and you get the data very easily and over large area. You think we should stop here, but in fact, it's not. If we're measuring chemical and physical data, let's look at what's the problem. Now, the first is that if you have the first year toxicology, you know that the chemicals in the environment may exist in different forms. And then different form of the same chemical, they have different bioavailability and different toxicity. That is to say, if you want to measure salinity, temperature, and that's relatively easy, okay? But if you want to measure chemicals, like organic chemicals, and inorganic chemicals like metal, it's not that simple and straightforward. Let's go through this. Now, so Kenny told you in his talk that mercury is highly toxic. But in fact, mercury in the environment occur in several forms. So Again, for elemental mercury, which we use elemental mercury in the old days, we use elemental mercuries in our thermometer. It's relatively harmless. And in fact, you would like to know that in the 18th century, if you got these got some problem with your guts, and then you cannot defecate, and then basically you go to the doctor in the UK, they'll give you elemental mercury to drink and a little bit, and then that will help you to go to the toilet. Then even now, of course, we are not doing it nowadays, but nowadays a lot of people with this amalgam in your teeth, right? If you want to repair your teeth and use amalgam is a mercury alloy, and you have it in your mouth, in your teeth, so you contact it every day, but it's relatively non-toxic. Likewise, for inorganic mercury, right? It's not readily absorbed and relatively non-toxic. It's toxic, but the toxicity is very low. However, if in the environment they change it into methyl mercury or dimethyl mercury, that change the picture tremendously, because these organic mercury, they are lipid soluble, they're highly toxic, they have a very high bioaccumulation potential. Remember the Minamata disease? Is that because they discharge the inorganic mercury into the water, and then the bacteria and fungi turn this into organic matter, okay? Organic mercury that causes Minamata disease is a big disaster. Now, that is to say, if you want to measure mercury in the environment, well, you have to collect the water sample and measure different forms, okay? In fact, if you look at some of the report by various environmental regulatory authority, they just report total mercury, which means nothing, okay? Now, if you want to measure everything in great detail, even for mercury, for one element, you measure different forms to estimate whether they are bioavailable, whether they are toxic, is a lot of work. Now, the other example is something like this organic pollution, like we call the persistent organic chemicals, like POPs. The most obvious case is the dioxin, dibenzofurane. These chemicals, they occur in very large area all over the world. However, when you want to collect water sample to measure them, they're in very low concentration, as parts per trillion, and some pollutant in parts per quadrillion. Well, under normal circumstances, you have to do a lot of work to concentrate this, and then before you can actually do this chemical analysis. And it's not an easy job, and because even you measure this, you contaminate using very clean apparatus to collect the water sample, make sure they don't stick to your water bottle, and then a lot of work to turn these chemicals into measurable form. Now, even you've done that, the chemical determination often very difficult, very tedious, and cost you a lot of money. Just like the case of dioxin, or even for metal, you have to extract this from the water. Afterward, you have to purify this, and then you have to concentrate this until it's in measurable concentration. And then before you inject it into a GC or LC or ICP, that involves a lot of work, very tedious, lots of money. Now, another typical problem faced by chemical and physical monitoring is that this temporal and spatial variability are extremely high. If anybody measured dissolved oxygen before, they know that if you go in the morning, early in the morning, like this curve, okay? Sorry, if you go in the evening, and then you'll find that the dissolved oxygen is maybe very low, because at that time, during the evening, the photosynthesis would be very low, and respiration rate would be very high. So even the phytoplankton would consume a lot of oxygen, and oxygen become low, okay? And particularly, they almost use up all the oxygen in the morning. So during dawn, it becomes hypoxic. The water dissolved oxygen become very low. And if you go in the midday, with very bright sunlight, when photosynthesis is the peak, you get very high dissolved oxygen. That is to say, for the same site, you have to take sample or measure dissolved oxygen almost every hour. You look at this curve. Your result depends very much on when you go to measure, when you take the measurement. You go in the middle of the day, it gives you a value of 8.5 milligram per liter. You go and in the dawn, 6 o'clock in the morning, 3 parts per million. So which one would you trust? So the only way you can do it to measure this at various time points, but again, this is Variability, this is measured 24 hours all over the world, not possible. Now, not only for dissolved oxygen, similarly for chlorophyll. So this is the data from variation from Finland. The variation in chlorophyll concentration, the Gulf of Finland. Gulf of Finland is a very small sort of inlet. You can see from travel from one end to the other, you take the hydrofoil, takes an hour. So you can see that that's from Tallinn to Helsinki, and then it's an hour's boat trip. And then you can see that it depends on where you go, the chlorophyll concentration varies. And same as the time, depends on when you go there, and then the time varies. And these, again, this data shows you the zinc concentration in Victoria Harbour in Hong Kong. Depends on which month you go. And you measure the concentration of metal in the water, it sort of varies tremendously. Now, that's not the end of the problem. The end of the problem is that you find a lot of chemicals in the environment, something like ammonia, metal, trace organic, and even trace organic, you may have PAH, PCB, and so on. So in the real world, these different chemicals will interact with each other. And then sometimes the effect may be additive. Sometimes the effect may be synergistic. Sometimes the interactive effect can be antagonistic. Now, that is to say, with more than 2 chemicals, you face the probability that this chemical may reduce the toxicity or enhance the toxicity tremendously. But it's very difficult to determine. Mind you, why we have to determine that? Because if you look at the over 95% of our environmental concern is not on the physical presence of the toxicants or the pollutant in the water, except something like microplastic or debris, rubbish, and then oil, slick, and so on and so forth. Something like, if you look at the metal, trace organic, and oxygen, and so on and so forth, we are concerned with the biological effect, not on the sort of physical presence. Now, but however, that's ridiculous because most of the environmental standard guidelines nowadays are predominantly based on physical and chemical parameters. At the moment, we are guessing what will be the effect based on the sort of the value of these physical and chemical parameters. But that may not necessarily be true. Guessing the effect, you do a toxicity to estimate what's the effect of pH, dioxin on fish is doable. But however, there's no way that you can look at in the real environment if dioxin interacts with metal, interacts with oxygen, interacts with ammonia. No way that you can do that. And yet you're measuring that, using a lot of effort and money to measure that. Now, again, this is, again, first year toxicology, you got to understand. You find presence of certain chemical in the environment does not mean it's biologically available. Just like what I showed you before for mercury and for a lot of compound, the bioavailability is not equal to present. Find something in the environment, something like, for example, some of the metals in the environment, they may be locked up in the sediment and then not available to the biological system. And then even if they're bioavailable, does not mean they have any effect at all, because your body can sort of help to clean up some of these chemicals. And then even they have effect does not mean adverse effect. Now, this is why you have a major problem in predicting biological effect and environmental consequence from the chemical data. You collect a lot of chemical and physical data, and based on this data, you try to guess and what will be the biological effect. Are we protecting the environment? Are we having adequate protection of environment? May not necessarily come true. So end up, you may spend a lot of money, a lot of effort, you end up with nothing. Just look at this guy. It's true. This guy spent a lot of time, lots of money in doing chemical and physical monitoring. Oh, he found that concentration of benzopyrene in water is 12 microgram. And the total pH in fish he measured is 569 microgram per gram. But when you ask the question, so what? What does it mean? Is it good, bad? At the most, he can refer to the US EPA standard and then the and something like or Hong Kong standard or China standard, whatever it is. Oh, it exceeds the standard. But is that true? But that is to say, based on the concentration, you cannot really predict what will happen in the environment. But if you turn this to the other more clever guy, the concentration of benzopyrene in fish will increase the cancer rate in the fish by 12.8%. And if you eat this fish, that will increase your cancer rate by 2.5%. We have to do something before it is too late, right? So these guys make a lot more sense because they will telling you what will be the consequence, right? In a more accurate way. Now, and people know about this for a long, long time, more than 20 to 30 years. And there's a global trend to supplement biological and ecological criteria in environmental monitoring and setting environmental standard and try to replace the chemical standard. But again, it's not that easy. We look at this biological monitoring, then see what's the advantage in doing biological monitoring in place of physical monitoring. Because certain biological responses are very sensitive to environmental changes and level of pollution in the environment. And I'll cite you a lot of examples later on. If you dip the fish into the and so on, so they're very sensitive. And sometimes they may exhibit a quantitative relationship. That is to say that they change in the enzyme level or change in the metal level in the muscles. And these changes is directly related to the environmental concentration. Then, as a result, measuring certain biological response may be easier and much more cost-effective than doing a whole range of chemical determination. Now, this is a hypothetical example. If you find some biological response, which is in a good relationship between the environmental quality, either dissolved oxygen, metal concentration, dioxin, and so on and so forth. If certain enzymes in the body have an established relationship to the environmental quality. So instead of measuring the concentration of dioxin or benzopyrene in the water, you measure the enzyme level of the fish in the water. Then they will give you a good estimate on the environmental level. At the same time, they'll tell you what will be the biological response. Now, in fact, biological monitoring is not a new thing at all. We've been doing this for more than 50 years. Everybody knows about the example of E. coli, fecal coliform bacteria to indicate fecal pollution. We don't go out to collect feces, but rather we collect E. coli and fecal coliform. And then if the concentration of E. coli and fecal coliform is high, that means high level of fecal pollution. For environmental engineers, we all use BOD to measure organic pollution. Instead of measuring the organic compound in the water and measuring different compound and measuring organic pollution directly, we only measure how much oxygen they consume per unit time, per 5 days, and so on and so forth. So we've been using this for more than 50 years. Now, It's very common for high school and high school kids to go to sort of look at the environment, to see the environment is good. And one typical example is that look at the tree, and then you can go to your sort of your country park or go to your garden to see if you tree, that means the air quality is pretty good, mainly because lichen cannot survive when the air is polluted. And in terms of water, and then if you go to a stream and you find rainbow trout, that give you a good indication saying the water is pretty good, because rainbow trout cannot afford to sort of survive in water with poor quality. So these are indicators. You find lichen, that means the air quality is good. You find rainbow trout, means the water quality is good. Isn't it much easier? Now, so the advantage of doing biological monitoring instead of chemical monitoring is that this accounts for environmental fate and biological availability. They will tell you the fraction of the pollutant that come into the environment, come into the biological system. And then, as I showed you before, the temporal variation is tremendous for a lot of chemical parameters. And then, but if the fish or the mussel is sitting over there, they keep on taking up these chemicals. So you measure the concentration of the same chemical in the mussel, in the fish, they will smooth out this temporal variation, provide a time integrated estimate on contaminant level. So instead of going every day to collect water sample, you go every month to collect the mussel sample. The mussel concentration, the concentration of pollutant in mussel will give you a very good indication on what's the average or time smoothen, time integrated estimate on the level of dioxin, on the level of metals in the water. That saves you a lot of analysis and time, and much more cost effective in terms of sampling and analysis. And what's important is that you find the metal concentration or you find the sort of dioxin concentration because it's actually being taken up by fish and by mussel. This can be more easily related to biological effect. So you're looking at the bioavailable fraction, which is the most concerned fraction. Now, there's two types of biological monitoring. First is bioindicator, and second is biomarker. Bioindicator is a biological indicator, a biological response at organismal level or above. That is to say, you're looking at the presence and absence, just like rainbow trout, like lichens. Look at the abundancy, look at the body burden of pollutant, look at the prevalence of this pathological symptom. If the environmental quality is not good, then probably or most likely you got more pathological symptom in the population. And then if the pollution is high, environmental condition is no good, you expect a decrease in species diversity, you got less number of species and so on and so forth. This would give you a good indication of environmental changes. Now, some of these bioindicators may be quantitative and some may be quantitative. Biomarkers, what is it? Biomarker is also looking at biological response, but at suborganismal level, just like molecular response, biochemical response, psychological response, physiological response, indicating a change in the environmental condition, either the presence or absence or the levels of pollutants in the water. Something like, if anybody have any experience going to body check, if you're old enough, you do any body check, you go to the, and if you got the problem, particularly with hepatitis B or hepatitis A, you go to a medical check and the doctor will take blood sample from you and look at alpha-fetoprotein. The alpha-fetoprotein is a protein in your serum. If it's high, that means you got liver cancer. And likewise, the ALT, AST, and these are also serum biomarkers for liver function. You got fatty liver, these sort of enzyme would be high. These are typical biomarkers. So you don't actually look at whether you have liver cancer or not, because liver cancer would be very difficult to detect at the early stage. But the alpha-fetoprotein and the ALT or AST, if it's high, that means it's likely to have liver cancer, that you got to go to have a more detailed medical check. So these are the typical medical biomarkers. And these biomarkers have now been used to monitor environmental changes nowadays. We all know that the muscles have remarkable ability to take up metals, right? More than 1,000 and 10,000 times higher concentration than in water. Now, when the metals goes into the muscles, they will induce the formation of a protein called methylphyolin. So again, instead of measuring metals, you measure methylphyolin.
Putol-putol, kanina pa ako din nakakaano dito.
Sorry? So methylphyolin and then indicate the exposure to metals. And again, a number of these mixed function oxidase, and then like EROD, if you find high EROD concentration in your liver and your fish liver, that means you've been exposed to PAX and PCB in the environment. If you find high level of acetylcholine esterase in the body, that means you've been exposed to organophosphates, the pesticide. So again, the measurement is relatively easy and give you very good indication without measuring these and the pollutants alone. And again, for some genotoxicant, if you make the fish or mussel or mammal has been exposed to this genotoxicant, this may cause DNA breakage. So again, DNA breakage or DNA damage would be a very good bioindicator for toxicants. A lot of these antioxidant enzymes like superoxidase, superoxide dismutase, peroxidase, if you're subject to oxidative stress, and again, these antioxidant enzyme would increase. So you can look at this enzyme level and tell you the history, and indirectly the history of the exposure of the animal to the chemicals, and also the level of these chemicals in the environment. Now, of course, just like what I said before, you can use BOD, E. coli, and sediment oxygen demand to measure the environmental quality in water, body burden of metals, trace organic, and we also measure red tide toxin in these mussels and oysters. And then all you need to do is to establish the concentration of these red tide toxin or trace organic or metals in the biota and the relationship in water, which is species specific. Once you establish this, correlation or regression curve, all you need to do is to take a mussel sample, take an oyster sample from the field, and then you measure the concentration of pollutant, which is relatively easy because it's sometimes 10,000 times higher than the concentration in water. Then you can estimate whether the pollution level is acceptable, high or low in the environment. And also, all these bioindicator can measure this dysfunction of individuals, and like the condition index, hepatosomatic index, that is what's the weight of your liver in relation to your body weight, gonatosomatic index, the sort of a size of the gonad in relation to your body, and based on the assumption that because if the animal is not in good shape, they spend less energy in sort of building up your body and building up your gonad. Now, your energy reserve and so on and so forth. And then pathological incidents. You go to an area, you find the fish got lots of infection, pathological infection. That means these areas potentially dangerous and with a lot of pollutant that makes that reduce the immunity of the fish. And then one very commonly used example is reproductive impairment is IMPOSEC. You know, TBT, fibrotidine, which occur almost over the world. And then the measuring TBT is very difficult. And also they got different forms. But because TBT can induce what they call the IMPOSEC in the gastropod, in the snails. So this marine snail, when they subject to TBT, the female will have a penis, have a male sex organ. So relatively easy. All you need to do is to go to the shore, collect these snails, and then crack it down and look at whether they got a penis, to look at the percentage of impulse set. They will give you a very good indication on the level of TBT in the environment. Of course, other like growth impairment, developmental disorder, change in species composition, decrease in species diversity and species richness, and so on and so forth. So again, these would give you a good indication on the health of the environment and the pollution level in the environment. For example, for hypoxia means a lack of oxygen in the environment. In a good environment, normoxia, if the environment is supplied with enough oxygen, you got more suspension feeders like this bivalve. You got high diversity, high species richness, and then you got more demersal fish living in the bottom, and then you got these animals with larger body size. But if the system is hypoxic, that is to say, lack of oxygen, all these demersal, all these suspension feeder will be replaced by the deposit feeder, like the polychaetes and so on and so forth. And then the size of the animal would decrease from macrofauna to myofauna. The demersal fish living on the bottom will be replaced by pelagic fish swimming in the water bottom itself, and then the phytoplankton will get smaller in size, become dominated by nanoplankton and microfactory. So you don't have to measure oxygen every day in the system. All you need to do is go and do a survey. They will tell you whether water is hypoxic or not. Now, in fact, a lot of countries is using that, like the NOVA, National Oceanic and Atmospheric Administration. They are now using mussels and oysters to monitor contaminants in US water instead of measuring metals in water. That's what they call the Global Mussel Watch, which started in the 80s. And then US EPA and are now assessing the ecological condition of natural resources instead of measuring the pollutants in these sort of areas directly. And a lot of regulatory authority are now using this benthic animal and biological indicators to monitor environmental changes. And also use fish histopathology symptom as the primary indicator of biological effect of contaminant exposure. Now, Environment Canada and Department of Fisheries and Oceans, they use bacterial count, and for red tide toxin, they measure red tide toxin shellfish instead of measuring red tide toxin water now, and look at body burden of mercury and pH, and look at the condition of benthic animal, indicate community changes. Same in Australia and New Zealand. Then, in fact, they are in Australia and New Zealand, they are pretty advanced in using ecosystem monitoring and bioaccumulation monitoring. And then they use the E-rod, which I told you before, as in flathead to detect pollution, and using the condition of benthic community for monitoring sewage outflow. And same as in UK and Europe, and then using histopathology symptom and using the E-rod, the enzyme, the acetylcholinesterase, the monitoring pollution, and do without measuring the chemical itself. Now, then I'll give you a brief comparison on the pros and cons of chemical monitoring. For chemical monitoring is very accurate and simple. You actually provide the data, something like the metal of, the concentration of pH is 0.163 micrograms per liter, right? For biological monitoring, it's less accurate. They can only provide you data, something like what's the concentration of the certain enzyme in the fish, and each individual fish may vary, okay? So less accurate. For chemical monitoring, as I said before, continuous measurement is normally easy. Put a buoy over there, put satellite monitoring, and so on. Biological monitoring, very difficult for continuous measurement. For chemical monitoring, the technique is more well established. For biological monitoring, the technique is less established. It depends on what kind of animal you have there. So chemical monitoring is very costly and very laborious in sampling. And whereas for biological monitoring, the sampling is much easier. For biological chemical monitoring, the concentration is low, making analysis more difficult. For biological monitoring, if you want to measure metals and trace organics in the fish, its concentration is higher, the analysis would be much easier. Now, for chemical monitoring, you measure certain things, just like what I said before, and so on. You don't know this chemical will enter the biological system. The biological availability is not known, and this is why the biological effect is not known. It's just based on guessing. But by biological monitoring, they indicate the biological availability directly. So what you see is actually the effect. Now, for chemical monitoring, as I showed you before, for various example, you got large variation for 2 or 3 times within a month. So you have to do regular monitoring. For biological monitoring, the time integration is built in. And then for chemical monitoring, it's very easy for you to compare the same data between location, between region. You want to compare the level of pH in the Port Phillip Bay in Australia with Manila Bay. It's easy. But for biological monitoring, it's not comparable because the biota, the species in Australia is very different from that in the Philippines. For chemical monitoring, you only base on the level of pollutant, and then you try to guess or predict what's the result, whether it's acceptable or not. But for biological monitoring, this gives you the direct interpretation of result. So, having said this, can we have the best of both worlds? Just like, you know, this joke that people like to have the good and the both works, and then both works is that you earn money from US, and then you got the US salary, you got a Chinese food, you got a Japanese wife, you got a British house. But unfortunately, you may get a sort of income from China, and the food from Britain, and the wife from America, and the house from Japan. No, that's not. Can we do that? So we have initiated, I told you before, the US have initiated the Global Muscle Watch program since the 80s. And globally, they collect muscles and look at a range of pollutant, including metals and trace organic in the muscles, and try to make comparison. But however, if you look at even the metals and the trace organics are biologically available in the muscle, the metal content is significant effect by physical factor like water depth, substrate type, temperature, turbidity, salinity, food availability, and biological factors like the seasons, lipid content, age and body size of muscles, and reproductive stage of muscle, and so on. Now, the other problem is the animal may be intolerant or affected by the prevailing environmental condition, which you don't know. Just like in Hong Kong, you put the mussel in Victoria Harbour, a polluted site, the mussel will die, okay? You put the animal in the sort of estuarine water, and then they may affect the uptake. So again, different species may take up different methods. And the limit of natural distribution over large geographical area like in the US create a big problem. In the Muscle Watch program, the Americans used 25 different species of bivalve from over 76 locations along the East Coast and the West Coast. So how do you compare the metal concentration and the toxic organic concentration in these 25 different species? And it's not comparable because the reproductive season is different. The susceptibility of environmental factor is different. So they've been spending 30 or 40 years in doing that and end up without much result. And then our group have developed an artificial muscle, a novel chemical device for metal monitoring. This just cost something like 50 US cents to develop this with a complex resin inside suspended in the artificial seawater and plug on both sides with permeable gel. And then there's using Kalex or PSTA, which they can absorb different metals. And then our laboratory experiment demonstrate the artificial mussel can take up a range of metal, including cadmium, chromium, copper, and zinc, lead, and mercury simultaneously, those dependent manner, without being interfered by temperature and salinity to any great extent, and reach equilibrium within 14 days. And the concentration of metal in the artificial mussel therefore reflect the average concentration of metal during the deployment period. So all you need to do, skip this, and all you need to do is to put this in the environment, and then after 14 days, you take this up and analyze the data, and then this shows a very good correlation with the mussels, that is to say, the take up and the accumulation of each metal in the artificial mussel is very similar and got a very good correlation with the mussels in Hong Kong. The advantage is that the metal content would directly reflect the average environmental concentration over time. And they only take up the biological available fraction and provide a time-integrated estimate and less affected by the physical factor and any oceanographic condition. So not limited by location and pollution level, can put it anywhere. So these new device enable us for the first time provide metal concentration in water all over the world, provide worldwide comparison for the first time, which the chemical analysis cannot do, and also the natural mussel cannot do. And then this work was featured in the Frontier and Ecology and the Environment. And then we've been commissioned by the United Nations, UNEP, and PAMC, and then IAEA, and for conduct various training courses in Hong Kong, Austria, Philippines, Indonesia, and Bangladesh, and also in Japan, and over the last 10 to 15 years. And then now the program has been extended over 29 countries, spanning all the 6 continents. Now, so for this monitoring, we have spent a lot of effort, but we still have a long way to go, but at least we make a start. So I stop here, and if you have any question, I'll be more than happy to answer.
Thanks a lot, Professor, for your sharing. Yeah, and a lot of experience sharing and personal reflection along with your long professional journey in this area. So then we may close the morning session. So you have enjoy your lunch for 2 hours. We may come back in 2 hours, okay? 2 o'clock in Hong Kong time and 1 o'clock in Cambodian time, okay? Right.
Okay.
All right. Thank you.
Okay,
thank you everyone
bye.
for your participation.
Thank you.
Especially that time and during morning, okay? Have a break. Enjoy your break.
Bye.
Bye.
Bye-bye.
All right. See you
Bye-bye.
soon. See you later.
Okay, welcome everyone. We're going to resume this afternoon section. I'm the chairperson, Professor Kenneth Leung, the Director of State Key Laboratory of Marine Pollution. First of all, I would like to invite Dr. Daisy Pandayo. She is representing PAMC. She would like to say a few words. Daisy, please.
Thank you, Professor Leung, and good afternoon, everyone. My name is Daisy Padayaw, so I'm with PAMC, the Partnerships of Environmental Management for the Seas of East Asia. First of all, I would like, on behalf of PAMC, I would like to express our sincere gratitude to the State Key Laboratory of Marine Pollution, the City University of Hong Kong, the Department of Applied Biology and Chemical Technology, the Hong Kong Polytechnic University, the Department of Science and Environmental Studies, the Education University of Hong Kong, for organizing this interesting and very informative training session on marine environmental research. And of course, I would like also to express our appreciation to all the participants for joining us today, and hopefully you can also join us tomorrow. This session is part of the pre-events for the East Asian Seas Congress, which will culminate on December 1 and 2. So we hope everyone can also join us during the culminating activity on December 1 and 2. And this morning, we have listened to some of the researches of the different universities in Hong Kong, like one of them, like the one that was presented on microplastics. And James Fong said that the university or his institute, or maybe personally, maybe their institute are open for collaboration. So hopefully we can forge possible collaboration with the universities of Hong Kong to share their expertise and knowledge to our participants from the region. And yeah, thank you very much. And I look forward together with the participants for a more interesting discussions this afternoon. Thank you, Professor.
Thank you, Daisy. Thank you for the sharing. We would like to thank her support and the support from Pansy for co-organizing this collab event. So this morning we have a maximum of 65 participants joining us this morning. So we hope the number will be increased over time. Right now we have 43 people, very good. So may I introduce to you the first speaker, Professor Rudolph Wu. He was the founding director of the Center of Excellence in Marine Environmental Research and Innovative Technology in Hong Kong. We call it MERIT. And then subsequently, he also established the State Key Laboratory of Marine Pollution based on the same theme of MERIT. And then in 2008, he successfully applied the status for the MERIT Center as the Regional Center of Excellence in Marine Pollution in East Asia Seas region. So for those who missed the morning session, he already talked about the pollution monitoring consideration. Now he moved on to talk about marine conservation and environmental management. It's a kind of new paradigm shift, some new ideas he wants to share with you. So may I give the floor to Professor Wu, please?
Yeah, thank you, Kenneth. Can you see the slides?
Yes, okay, no problem, very good.
Okay, okay, good afternoon, everybody. Welcome back after lunch. And this afternoon, I'll talk about the conservation and environmental management, a paradigm shift. So I'm trying to tell you the new concepts in addition to what we used to know about conservation and marine conservation and environmental management, and hope to have some insight on the environmental management in the near future. Now, as you may probably aware, and then human population increase, overexploitation of natural resources, habitat degradation, pollution, and biological invasion, climate change, and so on and so forth, all lead to drastic environmental damages and environmental disaster, including species extinction and the decomposition of and ecosystem failure, and so on and so forth over the world. So it become a major problem nowadays, and in particular, the effect caused by climate change has become a hot topic nowadays. Now, as such, the Convention of Biodiversity aimed to conserve biological diversity and sustain the use of these biological components. In 1993, China became a signatory to the CBD, and then Hong Kong joined them in 2001. Now, that provokes a new way of thinking. Say, in the early days, what we learned from the Convention on Biological Diversity, and in most of the literature, and in most of the environmental protection things, and then they aim to protect all species in our ecosystem whenever and wherever possible. Well, that's pretty holy, and I guess nobody would dispute that if possible, we should protect all species in the ecosystem and make a better environment for ourselves. And there's no dispute at all. But the question is that, is this possible? Now, in some place, like the sort of for example, in Great Barrier Reef, no problem at all, because there's not much anthropogenic activities, and then the environment keep us something like 50 years ago. But even so, and we are facing the problem of coral bleaching and things like that, and then for one reason or the other. Now, but in many places, if there's a pristine area, we keep it in the same way, and we have some difficulties. Not to mention that in many places in Hong Kong and many places in the Southeast Asia and elsewhere, and then we got lots of urbanized environment. So we have to learn how to live together with our environment harmoniously. Take Hong Kong as an example. Now, Hong Kong is a very small place. The total area of Hong Kong is only about 1,000 kilometers square, and yet it consists of all sorts of activity. Say, for example, we need to protect the Chinese white dolphin, which is the icon of Hong Kong, and then here, about here, and then we have to have a new airport, and then here, Victoria Harbour, we discharge the sewage water of something like 3.5 million people into this water. And then in this part, and then we urbanize, and we have yachting activities, swimming activities, and then fish culture activities, and so on and so forth. Now, the problem is that how do we deal with this situation if we have conflicting use of the environment? Of course, we then design different beneficial use in marine water of Hong Kong, saying that, okay, well, this part is for protection of the dolphin, this part is for human use, and this part is for swimming, this part is for monoculture, and so on and so forth. But is it okay? But when we have any development, it's quite often in Hong Kong, we got a major fight between the developer and green group. And in fact, it's not only in Hong Kong, it's fairly common anywhere in the world that whenever you have development, you clash with the conservation biologists, with the green group, and then they say, go away, don't do it, and so on and so forth. So how do we live together? Now, so for environmental protection, what we do is that now, the species from the species perspective. As I said before, can we protect all species? If yes, very good, no problem. We got no conflict and we live harmoniously with the environment. But if not, what is our priority? Now, so it's very common, of course, we have to protect the endangered species. Well, endangered species list on the red list of the International Union for the Conservation of Nature, like coral, like dolphin, like panda, black-faced spoonbills, and then in Hong Kong, we also protect the horseshoe crab and the Roman's frog, and so on and so forth. These are endangered species. Then what else? Of course, we need to protect the species or the habitat of high conservation value, something like the mangrove and seagrass and coral reef and so on and so forth. Now, thirdly, we got to protect the species that are vulnerable to human activity. Some animals are very vulnerable to human activity, and then if you do something wrong, they'll extinct. Well, then we ask the question, is it enough? So we protect all this. These are pretty obvious, and then nobody would sort of dispute that we should not protect the coral, Chinese white dolphin, and panda. But is that enough? Now, then some of the guy, even include an academic, I wouldn't mention name, is that every single species is important. In this ecosystem, every single species is important, just like bolts and nuts of the alphabet. Losing any one of these bolts and nuts will lead to big disaster. So we must protect all species, and then sometimes all individuals. Then I scratch my head, is that true? Let me think about this. Now, of course, when we say you protect all species, in fact, in my opinion, it's very easy. Your 3 years small girl can do that, because just say no to any activities. So don't touch anything, don't do anything. No, so you protect all the species, right? You don't need a professional to tell you what to do. Now, but I can tell you that from a species perspective, we should not look in this way, and some species are more equals than the others. Of course, you may, most of you have read the book called Animal Farm by George Orwell, and then the story tells about something like the animals doesn't like human being. This is why they gang up together to have a revolution, and then they said all animals are equal. Okay, but after they grab the power, and then they sort of they kick away the human being, and the animals become the boss, and they said all animals are equal, but they add on another appendix called, but some animals are more equal than others. In fact, that's true. In the ecosystem, some animals are actually more important than others. The first example is what we call the Keystone Species. Anybody been to a bridge in the UK or in Europe will know that there's a keystone here on the arch of the bridge, and there's a keystone. Now, you remove one of these break, does not matter. It's no good, but it's okay. But if you remove the keystone, the whole thing will fall apart. The same occurs in the ecosystem. A species that has a disproportionately large effect on its environment relative to its abundance. So we are not talking about the animals which are abundant in the ecosystem is important. They may occur in small numbers, but yet they are very important. Now, I cite you two examples. The first is the sea otters. They only have not a lot of sea otters along the western coast of America. The sea otters feed on sea urchin and also feed on the sea star. The sea urchin and the sea star feeds on this kelp, the macroalgae. Because of overfishing, the fishermen don't like the sea otters because they're competitive. They eat the fish as well, so they kill them off. But as the population drops, no, you can tell that immediately. If there's less sea otter, there's less predator, the sea urchin and the sea star will begin to grow. And these two echinoderms feed on the macroalgae. So if they are abundant, basically they finish all the macroalgae. So the system is like this. With the sea otter, everything in good balance. Sea otter feeds on sea urchin and the starfish, and they in turn feed on the algae. Okay, so with the sea otters, they control the predators of the giant kelp and also the macroalgae. So the system is good. They support a lot of animals. But if you take off the sea otter, the sea urchin and the sea star begin to grow in great abundance, and they sort of finish all the sea kelp, and then a system like this. So eventually the whole system collapses, and then they support no other animals. Another very typical example is that when you go to a rocky shore, you find this small animal called the limpets. Looks like an abalone, but it's not abalone. They do not occur in great abundance. You can find maybe 10 or 20 of them on a rocky shore. So you don't think that's important. But earlier on, way back in 1980s, and Professor Hawkins in the UK did a very simple experiment. He removed the limpets from the shore, and basically, after removing all the limpets, all the algae become overgrown. Because the overgrowth, they cover everything, so they kill off all the barnacles, mussels, and limpets, and so on and so forth. So you can see that you do disturb this, what we call the keystone species, can lead to dramatic changes in the entire ecosystem. Again, I'd like to emphasize these animals occur as one of the many members in the ecosystem. They do not occur in great abundance, but yet they are so important. If we remove them, the whole ecosystem will change, and then threatening the survival of the other species. Now, the other group is that what we call the functionally important species. Now, when we go to an ecosystem, we see all sorts of animals, but we actually know very little about what kind of function that they are providing and what kind of function that they perform in the ecosystem. Now, some species may play an important role in the functional ecosystem, including controlling the productivity, energy flow, carbon fixation, or they may regulate the nutrient and biogeochemical cycles, oxygen and carbon dioxide balance, and then sometimes they form important link between different trophic levels. Now, again, to give you some example, that's a sort of general description of ecosystem. You've got the consumer, producer, you've got the composer. Most of people, when in the conservation, they focus on the consumers and the producers, the things that they can see. But in fact, a lot of these decomposers, you may not like to hear the cockroach is also important because they play an important role in sort of nibbling these and the detritus and recycle them, okay? And mushroom, and then this earthworm, they look ugly. These detritivores and decomposers, they look ugly and they're inconspicuous in the environment, and yet they are important, performing important function in this ecosystem. Now, another example is barnacles. You all see barnacles, plenty of them now on the rocky shore. And then the barnacles, you may like to know the barnacle is the #2 highest energy flow in the marine ecosystem. That is to say, they channel a lot of energy from the pelagic environment into the intertidal. And also when they spawn, they would produce a lot of larvae from the norpi and then go into the water. That is to say, the barnacles are important, not only energy flow in productivity of the rocky shore. At the same time, they are also important in coupling the benthic environment and the pelagic environment. So if you kill off the barnacles, although they look ugly, and then they grow rapidly, but however, you're disturbing the whole energy flow, making the whole productivity of the rocky shore decrease, and also you decouple the benthic and the pelagic and link of the environment. Now, so disturb these species, which are functionally important, will impair the ecosystem structure and function, and then leading to changes in the entire ecosystem, and then pose a significant threat to the whole ecosystem, to the ecosystem integrity, and then nobody can escape from them, and then all species would be affected. Now, so I hope you then agree with me that we should hire sort of the we should accord the highest level of protection to these keystone species and the functional important species in the ecosystem, because any change in these keystone species or functional important species and all other species will be affected, and some may go extinct together. Now, if you look back to the very fundamental question, see why we need to protect our ecosystem from a human point of view is that we got to maintain different type of ecosystem services, which is desirable to mankind. That is to say, we're exploiting the environment in several ways. The first is that we need provisioning. We need the environment to provide food and natural resources to us. We need the environment to clean water and air for us. And then we need the environment to support a lot of this function that we want, like the crop pollination, energy flow, nutrient cycle, which are essential in our daily life. And then sometimes we need them to support the cultural services to us, like the recreational, we go diving, swimming, and then we go hiking and we see the mountains and things like that. Although they are not directly linked to us, but they provide good aesthetic value. And then, of course, we know that the environment provides a regulating function, control the climate and disease in many ways. This is why we need to protect our environment. We protect these ecosystem services. Now, coming back to this question, which I do not sort of agree, saying that every single species is important, just like bolts and nuts of an aeroplane. Losing anyone will lead to disaster. Now, if you look at this scientific side, the assumption from the ecosystem protection is that different species would perform different functions in the ecosystem, and then different species would interact with each other. And this is why we got to maintain a high diversity. There's no dispute on this. If you got a high diversity ecosystem, you got a high level of insurance to environmental disturbance. I'll come back to the mechanisms later. If you've got a high level of insurance to the environmental disturbance, you've got a high level of stability. That is to say that if you've got an ecosystem with high diversity, you'll be less vulnerable to human disturbance or to changes. And if you've got a low diversity ecosystem, this will affect ecosystem integrity and then an array of ecosystem function. Any change is more likely to decrease in the ecosystem stability and impair the desirable ecosystem services. That's the general principle. But let me show you an example. Now, that's you. You got 5 t-shirts, 3 pair of shoes, and 1 trousers. If your good friend asks you, hey, John, can I borrow a t-shirt from you? Oh, sure, 1 t-shirt. And then the other guy comes in saying, can I borrow another one from you? You say, oh, okay. So you still got 3 t-shirts. And then another friend comes in saying, can I borrow a pair of shoes from you? Sure, pair 1. You gave him 1. But if a guy came and said, can I borrow a pair of trousers from you? Oh, there's no way, right? Because the trousers is indispensable to you, whereas the t-shirt is dispensable because you got more t-shirts and then you can use. The same occur in the ecosystem. If you look at ecosystem function, now this is a hypothetical example. You got 2 predators, A and B, feeding on the herbivore C, D, and E. So A feed on C and D, B feed on 3 of them, and then C feed on F and G, D feed on F, G, H, E feed on G, H, I, and so on and so forth. Now, if we remove A, what will happen? So basically, if we remove A, so you got less predatory pressure on C and D, right? And then B would be actually very happy because B is competing with you, right? And then without A, B can grow better, and then C can feed on C and D. So if you look at removing A, although it's not desirable, but however, the only change is that, well, A is eliminated And then the whole ecosystem except A remain roughly the same. And then, in fact, sometimes B can also perform the function of A in terms of predation and controlling CDE and FGHI and so on. Now, but if the same system, but different sort of linkage and different relationship, A fit on C and D, and then B fit on D and E, and then the plant herbivore F, G, HI, and as the relationship as indicated by the arrow. So if we remove H, H is, well, one of the many plants in the system. If we remove H, what will happen is that immediately D got nothing to fit on because D fit on G, H exclusively, and same as E. So removing H means that you are also eliminating D and E. So we eliminating D and E, B will be also eliminated because B fit on D and E. Okay, A will be less affected because he would be fitting on C and F and G. And at the same time, if we remove H, because they are not competing for nutrient, and F or G may increase the abundance or decrease in abundance and so on and so forth. Now, you can see as opposed to the previous example, removing A, removing H will cause major devastating effect in the ecosystem, change the ecosystem completely. Now, then in the last decade, a lot of people did study on looking at this, what they call the functional redundancy. Now, because according to the general belief, every single species in the ecosystem is important, and then because they contribute to the stability. But in fact, if high level of redundancy occur within the same functional group, the studies find that further increase in diversity may not necessarily contribute to high ecosystem stability. And then for several study in the terrestrial system, they show that nutrient retention, okay, may be saturated at relatively low level of diversity. That is to say, provided you've got certain level of diversity, further increase in the species richness in diversity does not add on the ecosystem function at all, and does not add on with the resilience of the system at all. So once they go beyond certain limit, that will further increase will become functional redundancy. That is to say, further increase, they become redundant. Doesn't help much except the species itself. Now, if you look at the trophic relationship, in fact, if in the system, the weak trophic relationship is good, just like, for example, if I'm a euphagous animal, I feed on all sorts of animals. Okay, so if A is eliminated, I still got 4 or 5 different species to feed on. And then this is what we call the weak trophic relationship. They actually offer stability, okay, and high resilience. But if it's something like a very tight sort of relationship, the only relationship, just like this old couple, they rely on each other very much. So you eliminate one of them, the other will die. As opposed to something like one night stands, does not matter. You remove the companion, okay, find another one. Now, coming back to environmental management and conservation. Now, there's several questions that we got to ask before we manage our ecosystem in a scientific way. The first question is what kind of resources these animals exploit, and what kind of ecological or biogeochemical process that they regulate, what ecological function and services they contribute, and how important is their contribution. And lastly, equally important is, are they replaceable or non-replaceable? So without them, what will happen? Now, if we can have scientific answer to the above question, and then we can provide a sound argument for conservation of certain species, and then this can also afford us to prioritize species for conservation in a particular habitat, but not just blindly saying, oh, this animal looks cute, and this is why we need to protect them. The other animal looks ugly, well, does not matter. It's not. Now, So in the recent 10 years or so, there's a major paradigm shift of environmental management. Is from the species to ecosystem perspective. So don't get me wrong, I'm not saying that you should sort of destroy and kill off the species. That's not important. If possible, we should keep all the species. But the most important thing is that we got to know which species is most important, and we got to offer them the highest level of protection. Otherwise, the species that you like will diminish anyway. So in addition to maintaining the rare species or endangered species and overall biodiversity, we should dedicate our effort to ensure that important ecosystem function will be protected. Otherwise, all the target species that you wish to protect may be affected. And then we should also protect the ecosystem function in order for them to provide the desirable ecosystem services and species stay for us. Now, and this is why recently the major change is that we change from the species perspective to the ecosystem perspective. And the ecosystem management objective should focus on protecting functional group and functional diversity alongside with the protection of species diversity. As I said before, the functional diversity is more important because without that particular species, you cannot perform the function. Now, then the question comes in. It's easy to say theoretically, but in reality, it's very difficult. Let me go through these issues. If you ask how environmental stress and human activity that can affect individual species and community composition, we know a lot about this. You go to have a literature search, there's thousands of papers, thousands of publications, thousands of evidence to show you that in what way, what kind of environmental stress can affect what species and what kind of disaster they can lead to, and they can change communities, composition, so on and so forth. That's not the problem. But if you ask and search the literature, how human activity may affect ecosystem function. Now, there's only very limited study has been carried out, and most, if not all, these studies are carried out in terrestrial ecosystem. Whether these results can be applied to aquatic ecosystem, to marine ecosystem, remain almost unknown. And even for ecosystem function of terrestrial ecosystem is still at the rudimentary stage. Now, so if you want to apply this sort of known scientific evidence to other places, there are only limited study applicable to other places, something like China, tropical and subtropical regions. They haven't done any sort of this study before. So I'm not sure we can use the same sort of principle to borrow these research results on something like temperate region from Europe and from American and apply them to this part of the world. We actually don't know. Now, another important question a lot of people neglect in environmental management is that some species may be very sensitive. Some species may be very tolerant, just like this guy. And then if I ask you to judge, to guess, so this guy, you give him a poison and he can probably survive. This skinny guy, you give him a little bit of poison, you kill him off. That's what we call the resistance. Again, we know quite a lot about this. So that is to say, we know what species are resistant to environmental damage. Roughly, we know about this. But we know very little of whether they will come back or not after the disturbance. Just like this slide. For example, if they're highly resistant, but disturb them unless the disturbance is very high. Otherwise, they will remain the same. But for some species, you disturb them, and then they will sort of go down, the population go down. But after the disturbance, they will come back quickly. Just like bacteria and COVID-19, you remove 99% of them, they'll come back tomorrow. All right. Now, this is again something we do not quite understand. So some species, like opportunistic species, like the barnacles, like the COVID-19, like bacteria, they have a very remarkable ability to grow and recover quickly if we remove a large proportion of them. That's what we call the high resilience. They can shoot back. And then just like this roly-poly, you turn it down, it comes back within seconds. Turn it down, come back within seconds. That's high resilience. But some species, most species with low growth and reproductive potential, they may collapse even if a small proportion of population disturbed. That's what we call the low resilience, like the Chinese white dolphin. A lot of animals, because their reproductive potential is so low. So even if we remove 1/3 of the population, the whole population will collapse because what they call the reproductive encounter. Removing 1/3 of them, they fail to find their counterpart for mating, and the whole population collapse. You don't have to kill all of them. And then the whole population will collapse, and you don't know. It's very difficult to predict. Now, so we have to ask, what are the functional role of the species in the ecosystem? In what way were important to us and our ecosystem? So as I said, Chinese white dolphin, what's the functional role? The functional, what the barnacles, limpets, seahorse, and red tide. So how vulnerable are they to human activity? What is their resistance? And how soon will the population restore itself to the original state after perturbation? The resilience, unless you know the resistance and the resilience and the functional role, otherwise we are not offering any scientific ground for protecting certain species in the environment. Say, for barnacles, you scrap 90% of them, they come back in the next season. Now, so it's not empty works. One good example is fisheries management. We all know that human beings have spent a lot of effort and scientific research into fisheries management. And this is why we work out what they call the sustainable yield. That is to say, we can go and fish, that is to say, at the same time, destroy the environment, destroy certain species, kill certain species. And then until certain level, if you keep on killing certain amount of fish, harvesting certain amount of fish, say 20% of fish of certain size from the environment, it will be sustainable. You keep on doing that, your kid, your grandkid keep on doing that, we still got the same fish, same number of fish in the environment because they can come back. That's called the maximum sustainable yield. In actual fact, for salmon and for pike, we all have data for this maximum sustainable yield. But after overfishing, you kill more than they can afford to, and then the whole system will the whole population will collapse and extinct, deplete. Okay, so if we apply this system in or the same method, same approach to environmental protection, that's very good. So that is to say, we can actually have scientific evidence to know how much we can take off, how much we can exploit per unit time. The system is still the same. Oops, sorry. Now, so to sum up, we need the scientific information required to bring us forward if you want to do ecosystem function management. So the question is, what will be the environmental consequences if a given species is affected by human activities? Second question, will ecosystem be compromised? If yes, to what extent? Does it matter? So if we can answer the above question, we will be able to manage our environment based on the science rather than passion, rather than people saying, oh, don't touch anything, don't kill this, don't kill that, and then don't take this, and we'll take everything. We enable the decision makers, stakeholders, and the public to make informed decisions with respect to conservation and sustainable development, not just blindly saying that I like this species, and this is why we need to conserve this. Now, so in actual fact, 5 years ago, China has formed a working group to look at this ecosystem function. And then I was a member, and then we tried to push a major scientific study to answer this question. And then the first pilot pond that we use in Bohai, and they start these scientific studies already several years ago. The whole idea is to identify the keystone species and functional important species. Species responsible for energy flow, productivity, carbon sequestration, nutrient biogeochemical cycle in the Bohai system as a model. And then the second task we do is try to elucidate the relationship between biodiversity, ecosystem function, and ecosystem services in Bohai. And then we identify possible human threats to species of high conservation value, keystone species, and important functional species. And then we assess the resistance and resilience of these species to the threat presented to them. So we hope this Bohai case will form a role model for the other part of the world, which never done before so far. And then to show environmental managers how to manage our ecosystem in a rational and scientific way by looking at ecosystem function, not just using the old school of thought, just protecting individual species. Now, understanding our ecosystem in terms of the species composition, function, and services that species provide is important, is fundamental. And then we be able to assess and manage the risk of human activity on biodiversity and ecosystem functioning, and determine the protection priority and development strategy in a scientific way, so that both underprotection or overprotection can be avoided. And for those who are working in environmental management, not only environmental science, we know that both underprotection or overprotection is not desirable. Why? I'll show you an analogy. Say, you're a rich man in your house, you got a bedroom, you got a kitchen, you got a garage, but you need to take care of your bedroom, clean your bedroom, kitchen, and garage every now and then. May I ask you a question? Would you like to keep your kitchen and your garage as clean as your bedroom? Yes, of course you can. You go and clean it up every day like your bedroom, not a problem. Avoid the car coming in, clean your car first, and so on and so forth. And clean your kitchen every day. But is that necessary, right? Because what we call the functional use or beneficial use, the use of bedroom as to go to bed, go to sleep, it got to be absolutely clean. Garage does not matter. You drive your car in and then you walk away. Of course, it can't be too dirty. Same as a kitchen. Likewise, the water quality for protecting coral should be very different from the water quality in a sub-harbor port, because harbor port, your major function is for sort of for hosting the ship and cargo and so on and so forth. So the water quality required is not as strange, should not be as stringent as coral protection of coral reef. Of course, as I said, you can, but whether it's worthwhile or not is you think about this, okay? Because it costs you money, costs you effort. Now, so this ecosystem approach and functional approach will provide a sound scientific basis for us to evaluate the risk and acceptability of development. Whenever you got a development, you know what is the risk and whether it's acceptable, noting that ecosystem function and ecosystem integrity must, at the very least, be protected in all cases. If you destroy ecosystem function, ecosystem integrity, you get nothing. Now, because we have very, very limited knowledge on ecosystem function, ecosystem protection, and so on and so forth, and ecosystem integrity, it is generally assumed, in fact, in Australia, saying that if you protect 80% of the species, would be equal to protect the ecosystem's integrity. But that may not be true. As I said, for argument's sake, if the other 20 species happen just in the unfortunate event, it happened to be the functional important species or the keystone species, you're not protecting ecosystem integrity. So these scientific sort of knowledge would enable us to have a good balance between development and the environment. Now, to summarize, we should manage our environment based on science, in addition to passion. A lot of green group manage the environment or protect the environment based on passion because I like it, okay? The people like different the environment in different way, okay? And it's a very subjective. In addition to conservation of endangered species and species of high conservation value, we must also identify keystone species and the functional important species and accord them the highest level of protection. Otherwise, you'll be protecting nothing. And then we got to work out the species-specific resistance and then the species-specific resilience before we can predict the risk of human disturbance on biodiversity. In the absence of such knowledge, however, the precautionary approach should be used. We should take precautionary approach. We don't know, don't do it for the time being, until we find out all this information. Now, with this, I'd like to come to an end to my talk. And then I hope with this approach, with science as a sort of foundation, environmental protection and the development can go hand in hand together. Thank you.
So thank you, Professor Wu, for this very inspirational sharing on this new thinking about marine conservation by looking at the ecosystem functions. So I would like to invite participants to ask him question or share your own opinion. So you can put down your question in the chat room or just use the raise hand function so that I can identify you, or you just need to speak loud and you can ask question or give comment. So you may start now. Maybe I start with a question. It seems that those keystone species or species with important function may change over time in the same area. Then would this present a challenge in terms of management?
Oh, yes, it's a good question. But I think we are far, far away from answering and from being able to answer your question. As if you look at the literature, look at keystone species, there's only less than, to my recollection, there's only less than 10 keystone species or 20 keystone species have been identified over the world so far, okay? Now, so if you do not understand what is the keystone species in the ecosystem, and then we cannot manage the environment, let alone the question you ask is the second step, and different stage, and then the keystone species may change.
And also I have a question in mind that to understand what we have in the ecosystem will depend on our survey effort. So no matter you're using the trait-based survey or functional-based survey. So given that all the governments in the region with limited resources, how can we overcome this problem?
There's no hard and fast rule in actual fact. And what I hope is that the Bohai pilot study and will publish its result and in another 3 years' time, for example. And then we can borrow a lot of these examples from the Bohai study. The China government actually spent a lot of money, inject lots of money in doing that. And then, and that would form an good example. And because of it's also in Asia, and because in Bohai, they also cover different habitats. So they may provide a lot of useful information, not necessarily directly applicable, but at least to enable us to have a better guess, I would say. We have a long way, in fact, we have a long way to go. And this is why we call it a paradigm shift.
Okay. Okay. So I would like to see any students, participants would like to ask questions or give comments. I saw one on the chat room from Heldai Lakota. She is asking, just like in any impact assessment, we will be asked as to what can be a change in function that is deemed acceptable. Can this be qualified?
Oh, yes.
Question.
Yeah, thank you. And this is, again, a very good question. So the one who raised the question must be an environmental manager and very pragmatic. And then what if we got to find, if we predict some change in their minds, in the ecosystem function, and then that's deemed to be acceptable or not acceptable, it depends on to what extent and the beneficial use of the site in question. For example, if I may cite an extreme example, if you want to protect the coral reef, any change in the ecosystem function of coral reef, well, may not be acceptable. But the same change may be acceptable if you do on a swimming beach, and then the larger change can be accepted or become acceptable in sort of a harbor, for example. But again, is a question which is not only related to science, but also a lot of the human judgment and the depends on the culture and so on and so forth. It's extremely complicated.
So it also depends on this beneficial use you just mentioned.
Yes. Yes, so you have to make reference to the beneficial use that you decided.
Yeah. So any other questions? Or Hyundai, actually you can speed up. So you can show your face and talk to Professor Wu if you like.
Good afternoon, sir, Professor.
Yeah.
Is this okay?
Yeah. Hello.
You can hear me?
Yes.
Because this is something that we are always, we often see ourselves under debate because there are different perspectives in economics, in ecology, and well, those are the most important fields that usually would go into debate for this. And if it's economics that comes into play, the ecological explanations usually are shelved and they're left behind. So your perspective actually on lobbying for we must happen already. Say there is so much development in the new normal. I think it doesn't happen only just here in the Philippines, but elsewhere as well. So for it to be effective, it has to be passed as a law.
Yeah.
And before it becomes that, there'll have to be many cut-offs. There'll have to be a lot of balancing that has to happen.
Yeah. Yeah, I totally agree with you. And then, in fact, as I always say, the environmental management is a very complex issue. And then people, I told my students, and then doing environmental science, if you think environmental science is almighty, you're wrong. And then, normally, under most, if not all circumstances, environmental economics is more important. Well, as I said, I mean, you can actually keep the environment as clean as your bedroom anywhere. It's how much effort, how much money you'd like to put in. And we can, in fact, remove all the waste from our wastewater, right? And then up or down to the level, just this cup of water. It's a matter of money. And then economics will be again override by environmental politics. Well, you get the politics, a lot of these are not actually considering environmental economics or the environment, but rather politically, they think it's correct, okay? And then just like a lot of these minority, something like in the US, for example, they protect the Indians, okay, at any cost. but the same sort of protection will not afford to the other. Likewise, in Australia, and the government is prepared to put lots of money and to protect, to cater the need, the environmental need for the Aborigines, but not for the others, mainly political reason. So again, it's a very complicated issue, and yes, and this is why there's a highly interdisciplinary and topic.
Thank you very much, sir.
Yeah,
Thank you very much for the discussion. Okay. Once again, thank you, Professor Wu, for giving two very insightful talks today. And he will give another talk tomorrow. We're looking forward to. So now, may I invite the next speaker, Leifen Jin Ning. He is come from the Polytechnic University of Hong Kong. So let me see my script first. He is currently an assistant professor at the Department of Civil and Environmental Engineering at the Hong Kong Polytechnic University. His main research area includes air pollution and human health, airborne and foodborne transmission of antimicrobial resistance and pathogens, and pollution-induced immunosuppression in Chinese white dolphins. He using the Chinese white dolphin cell lines he isolate and culture in the lab. Today, he will provide training under the topic of toxicity assessment of chemical mixture. He started this area of research when he was doing his PhD in Queensland University under Beata lab. So now may I invite Jeannie, Nathan, please.
Oh, thanks, Kenny, for your kind introduction. Today, I will briefly talk about some concepts and some application, okay, very briefly, and try to make it this complex mixtures simple, okay, for as a training purposes, okay. So actually we're experiencing multiple chemicals in our daily life. So a very good example is actually what is good for tonight, okay, Friday happy hours, the cocktail, okay. So which includes a lot of ingredients, right? And the combined effects of these things makes our job, brings joy for us, and also if too much, okay, if too much, there may be some cause some health problems. All right, so this is the same, which is also true to the environment, okay. Similarly, our marine environment, aquatic environment, drinking water sources, all sorts of things, our wildlife, our human bodies are exposed to on the bad side, okay. It's experiencing this kind of multiple stress of the and synthetic and natural organic chemicals, as well as their transformation products, which may be formed after being released into the environment. Okay, some including what we have known as personal care products, right? Pesticides, herbicides, yeah, natural hormone, and some mimics, right? And well, just to name a few. Okay. Now, so as we know, so in the commerce there are more than 100,000 chemicals are there already. So how much have we really known on the front? Think about an iceberg. Okay, this is the chemical universe. So how many have we really known? How many have we known? Okay, so but the important thing is, do we really need to identify them? Okay, do we really need to identify those unknown? Based on what? Now this is the main questions I want to bring forward at the very end, in the very beginning. Okay, so now, so there are two views. Okay, two views of chemical mixtures separately.
Dr. Jin, are you sharing a PPT?
Yes.
But we cannot see it.
Oh, sorry.
Yes,
is it right now? It's okay now.
Yes.
Okay. Then maybe a cocktail. Okay. So the chemical universe in the world. All right. All right. So there are two views. Okay, from a chemist's view and the toxicologist's view about what mixture, the perception. Okay, on mixtures. So chemical analysis, chemists, okay, develops a different instrumental analysis to measure metals or whatever on a target way, conventionally, to analyze those regulated chemicals, okay, or what they want to measure to their interest. So it's quantitative for key target chemicals, right? But there are also unknowns with the difficult and work intensive to identify, but it can be, okay, solved, okay, with the advances of so-called non-target analysis. But from a toxicologist perspective, okay, we are really trying to fully integrate these chemical groups, okay, to summation of groups of chemicals with common mode of action. So the basis is on what we really view are, so on the toxicology perspective, like dioxin-like chemicals, which are acting commonly on area hydrocarbon receptor, or those chemicals, or all together working on commonly acting on oxidative stress or as hormone mimics. But so the toxicology try to have an integrated mixture effect measurement, okay, mixture effect measurement using a common endpoint. But this is an integrative way, but the drawbacks is the single chemicals cannot be resolved. But how can we really complementary? But actually, these two can be complementary to each other to solve the question, to solve two major questions. So what are the combined effects of all sorts of chemicals in the environment, in the water, in the sediment, right, in our food, or also, and the other thing is very important is now how much effects can be really explained by identified chemicals, or for example, what we analyze can explain how much of the total effects, so that we can prioritize individual chemicals, whether they are important or of lower importance. Okay, so then now, as we said, we based on this kind of toxicology perspective, we need something to measure on the endpoint. Okay, so the adverse outcome pathway and the toxicity pathways provide this kind of conceptual framework, so that we can now. So with the advances of 21st century toxicology, now we know this kind of cell response up to also higher level of our organization, up to ecosystem health. This is a promulgation of biology effects. Now, as Professor Wu Professor Rudolph Wu just talked about, so the ultimate goal, okay, the ultimate goal, protection goal, is targeting the ecosystem health. Okay, so but they're very difficult to measure. Okay, but they are very difficult to measure. Now we can do something, okay, with low complexity acids for invertebrates like copepod that commonly used, that Professor Kenneth Learn are experienced in. Okay, so now, but we can also down to this level cell response, which can be an integrated bioanalytical tools can be used as early indicators of hazard potential of chemical mixtures and are indicative modes of toxic action, like targeting this kind of initiating events. Okay, as we said, you know, for example, induction of xenobiotic metabolism, or some more specific receptor mediated effects like estrogen, right? Those hormone receptors, right? And also some reactive toxicity like DNA damage, inflammation, oxidative stress. Okay, then all the way up to some apical events like cell death. So we can do this kind of cellular toxicity, cellular assay, as well as some low complexity like algae toxicity assay. Okay, so can can be used in a high throughput way to allow us for more rapid screening of the mixture effects contained in complex environmental samples. So this is a typical workflow, okay? Typical workflow. Like we start from dispensing of those target cells we want to measure, right? Prepare the dosing place, and we treat the cells with the individual chemicals and mixtures of chemicals, as well as environmental complex mixtures containing unknown chemicals. Okay, then we do this kind of so-called dose response analysis, concentration effect analysis, and measure the endpoint, like using some reporter gene or enzyme analysis to measure those kind of responses as shown here. Okay, now before we move on to more complex mixture, okay, toxicity prediction or whatever. So here we need to first understand, okay, very important concept of this kind of concentration response. Now this is actually from a pharmacological perspective, in the Paracelsus or the very Asian Italian, okay, Italian pharmacist, okay. So his famous notion is all substances are poisons. So there's none which, so only the dose that makes a poison or a remedy, okay. So basically we do this kind of concentration response or dose response. The x-axis as the concentration, okay, increasing concentration of a substance, okay, for example, pesticides, right? And then the effects, the y-axis is the increasing effect of, for example, the cell death, inhibition of photosynthesis, right? In the case of photosynthetic pesticide inhibitor, okay? So we do, not for mixture toxicity evaluation, very important that we need to have certain benchmark, okay? Like so-called EC50, effective concentration of 50, which means the concentration at which 50% of the effect, okay, of the maximum occurs. Also, we may use EC10, okay? Now, there are also two very important metrics, so-called no observed effect concentration or lowest observed effect concentration within this kind of the control range. Now, we will use this as an example for later. They're very important concepts just to bear in mind. Okay, later we will talk about something from nothing. Even those chemicals at their no observed or lowest observed effect concentration mixed together, they may still produce something, okay? So-called something from nothing, right? Now for this kind of concentration response evaluation, this software, okay, commercially available software called GraphPad Prism is just a really good tool to allow you to fit this kind of nonlinear sigmoidal equation. Okay, so which it is also visually appealing and it has great handbooks, right? But you must bear in mind that for modeling, okay, trash in, trash out, garbage in, garbage out, it does not free you from understanding what you are doing. Okay, we need to understand the basic concept, right? Okay, now we have talked about how we evaluate individual, okay, individual and the chemical. Then we think about the mixture, okay. There are the basic concepts of mixture toxicity. So how a bunch of chemicals act together, okay? How can we predict them? And there are some basic concepts behind. So the joint action of chemicals depends on what? Depends on the site of action, target site, and the mode of action, which we have explained here. Okay, specific estrogen mediated receptor, right, or whatever. Okay, so now basically there are four categorizations. If the chemicals do not interact with each other, and they act on the similar joint on the same target site. For let's say target on this a group of chemicals, all commonly targeting the area hydrocarbon receptor or targeting the hormone receptor, the same hormone receptor. So eventually they will exhibit a simple similar action, okay, joint action, so-called concentration addition, okay, in the follows this way. Now, if those chemicals are working on different target sites, now one is working specifically on photosynthesis inhibition, one is non-specifically targeting cell membrane, but when they work together on algae, okay, for example, on a plant, so they may display, okay, dissimilar joint action, which can be described by the so-called independent action ion model. Now, these two modes can be mathematically described, okay, but more complex things happen if some chemicals, they may have some interactions are present. They may have more, but still on the same site, but they will exhibit a complex similar action. Okay, but for those interaction that are working on different target sites, they may have dependent action. But from the literature, okay, so many decades of research. So these two are quite rare, okay, in the environment. So most common modes are these two, and concentration addition, okay, we can guarantee that it explains very well, okay, the joint impacts of a bunch of chemicals in the environment on certain biological endpoints happen in the environment. Okay, now this is a typical example. Okay, back to it's not 2 decades ago, right? Working on these authors working on endocrine disruption. Okay, trying to understand the eight estrogen receptor activator. Okay, so all individually they are below their threshold level, but once they mix together as experimentally determined here, so it is very close to what can be predicted from concentration addition. Okay, now because simply they are working on the same target. Okay, for example, in this case, it's estrogen receptor. It's a hormone mimic, right? So there are also a lot of other examples, okay, for something from nothing, right? So for chemicals with the same mode of action, I think we don't have to go through the details because we will share this slides later. Okay, also something from nothing for chemicals with different modes of action, okay, described by independent action ion model. Okay, so just a little bit a wrap up. So independent action, okay, strictly valid, okay, only for compounds with different modes of toxic action, and in most cases different targets, okay, target size. And theoretically, in principle, if compounds with dissimilar modes of action are mixed, each in concentration below threshold of effect, the mixture cannot have a significant effect. But in practice, it's not that. So, okay. And also for CA model, okay, typically holds valid for chemicals with the same mode of action. So if compounds with the same mode of MOA are mixed, each in concentration below threshold of effect, so the mixture may have a significant effect, okay, which you have seen from the 8 compounds for the estrogen receptor induction, okay, and also which is also independent of the mode of action. Most apply the concept in ecotoxicology because, as we have seen over the decades, so the mixture effects in the environment, okay, triggered by known chemicals really follows this model, okay, which makes life easier, okay, because it's mathematically describable, okay, in a simple equation. So for these two, okay, so quite rare. So I don't have to repeat it again, okay. So think about Now, then we really need some quantitative thinking, because talking about prediction, okay? So think about two component mixture, chemical A and chemical B, okay, when they mix together, okay, so-called binary mixture. So here is a top concept is so-called Tox unit. Now, so we use this kind of isobel diagram to describe, okay, what is under what kind of situation. So these two chemicals can act on a concentration addition way, which also when it goes for antagonism or independent action or synergism, okay. So more than additive. Antagonism means less than additive. Okay. So the toxic unit TU. Now think about it. We do those concentration response for each of the chemical A and chemical B, and with a derived effective concentration, let's say EC50. Okay. So then we, for example, take 3%. No, sorry, 30%. Take the chemical A at the concentration of 30% of the EC50. Okay. Then take 70%. Take another chemical, the chemical B, at its concentration of 70%. Okay. The fraction needs to be the summation of these, because two chemicals, one 30% or 70% or 50% or 50%. Let's say the summation as one. Now, if the toxic TU1, okay, toxic unit plus toxic unit, the summation of the toxic units of these two chemicals equals 1, then we can say they strictly follow the concentration addition. Okay, but there are some cases these two plus sum together may be greater than 1. Okay, so which is less than additive. And or greater than 1, less than additive, or less than 1 is so-called synergism. Okay, more than additive. Now, there are some example of synergistic interaction. So, for example, a very traditional example of atrazine, a banned herbicide, can in interaction with organic phosphate pesticide. Okay, so they may exhibit the synergistic more than additive. Okay, so the hypothesis behind is maybe the atrazine induces enzyme that catalyze the activation step and thus produce more active agents. So the combined effects of these two, okay, pesticides and pesticides and herbicides act more than additive. Okay, but they are very rare examples, especially in the environment when it is diluted in so many chemicals altogether. Okay, so the concentrations addition still hold. Okay, now then think about it. If the components are expanded, okay, from 2 to 18, let's say, okay, in this case, the 18 atrazine analogs, okay, are all inhibitors of photosynthesis by binding to photosystem 2. So with a common target, common mechanism. So we do this kind of prediction. Okay, we predict the joint effects using the independent model. Okay, an independent action IA model. We also do the CA prediction, which is the dashed line. Okay, then we really mix together and test it on the algae. Okay, and see the photosynthesis combined effects of the 18 chemicals. So it really follows very well for the concentration addition because they have the common target, right? So how about independent action? Okay, so now 16 in this case, 16 dissimilarly acting substances. Okay, some specifically targeting the photosynthetic system 2. Some are non-specifically targeting other parts of the algae system. Okay, so they pretty well follow the independent action model. All right, so now this is not only the mixture. How about the mixture typical environmental pollutants in the real environment? Okay, so they are not only applicable for mechanistic endpoints and a low complexity system, as we just talked about before, okay, and for the algae. But even for long-term sublethal effects in fish in vivo, in this case, is an induction of betallogenic, okay, in male fish as a measure of estrogenic activity, okay. So with natural and artificial estrogens, okay, like estradiol E2, which is naturally occurring, right, in fish and in humans, right? And also a contraceptive, like a synthetic hormone, estrogen mimic, so-called E2, okay, mixed with xenoestrogens, right? These, now we have known this kind of bisphenol A, okay, they act in mixture additively. This is a very typical example, okay. Then also, now, these chemicals are artificial designed mixtures, okay. Then we talked about all sorts of environmental real mixtures of chemicals occurring in the environment. Now, how about we mix the chemicals, okay, those regulated chemicals, okay, in the under the drinking water guideline values in the ratios of the drinking water guidelines, as well as mix those chemicals in the ratios of their occurrence, their concentration ratio in the real drinking water. Now, so we test them on the simple bioassay, so-called microtox assay. It's a bacterioluminescent assay, okay, to measure the chemicals disturbance of the membrane, okay, and kind of as a measure. Okay, so we do this kind of equal potent mixtures and mixtures in ratios, okay, in the drinking water guidelines or as the occurrence in the real water sample. So basically all are very close to CA. Now also another example is for surface water, right? So the mixture model, toxic model of concentration addition has very good predictive power, okay? But specific chemicals drivers of mixture effects, right? And also different chemicals for different endpoints, okay? So we will talk about how we can really identify or quantify the contribution of known identified chemicals to the mixture effects in water or in biological samples. Okay, we will talk about those algorithms later. All right, so now, as we know, okay, the aquatic environment contains a diverse range of contaminants and transformation products, okay? So if we inject a water sample or inject a sediment sample, biological tissue sample, okay, into the GCMS or air in our instrument, okay, typically we will identify 20,000 peaks, okay, many of them unknown, with unknown identity and quantity. So so in vitro bioassays can complement the chemical analysis to measure the entirety of the cocktail effects, okay? So the mixture effects by in vitro bioassays quantified, but quantitative agents not identified. So that's why we need to better understand the link between chemical analysis and what we can identify, target or non-target, and what we can measure for their combined effects. So, and also need to think about the mixture models that we can use. Is it applicable for, so for example, the concentration additive? So in the next part, very, very short introduction about the so-called iceberg models. So to help us quantify, okay, how much of the identified chemicals, known chemicals, contribute to the whole mixture effects. Now, so in a case analysis from the Germany, okay, so those scientists sampled water samples, surface water samples, along a gradient, okay, along with a gradient from upstream, relatively pristine, okay, and to the outlet of the wastewater treatment plant to collect the effluent, and all the way to the downstream potential with dilution, but still maybe to some extent being affected by this wastewater treatment plant. Okay, we do this kind of effect analysis, bioanalysis okay, for photosynthesis, algae toxicity, or oxidative stress or whatever, okay, to characterize the mixture effects represented by the whole iceberg, okay. So we'll derive this kind of EC for sample, okay, so-called tox unit of the sample. And also we detect individual chemical concentration, okay, especially for, in this case, it's target analysis for regulated chemicals under current regulation surveillance. Then we also tested these chemicals in the bioassays to derive the effect concentration, okay. So we can summarize summation them to for the toxic unit of the chemistry toxic unit of the identified chemicals as the tip of the iceberg. So we want to know how much of the tip have we really seen, okay, which means how much of the identified chemicals, how much of the entire effects can be explained by the identified chemicals. So for chemical analysis, okay, they follow the list of the regulated chemical inventory, okay. So they use this kind of ARC mass analysis to quantify the concentration, okay. So pretty straightforward. And then they also fingerprint of the single chemical compounds for their effect potency, okay, to characterize this part, okay, so that we know can characterize the mixture effects of known chemicals, okay. So in this case, like for example, photosynthesis inhibition, right? So the majority of the identified herbicides can explain the majority of the mixture effects. So we can also prioritize according to their contribution. Prioritize diuron or terbutaryl as in explain most effects. So which means they are the greatest risk drivers. Number 4, the mixture effects on the fish embryo or oxidative stress. So the identified chemicals only identified regulated chemicals only explain a very small fraction of the entire mixture effects of the water samples. All right, this is another example during my PhD. Okay, we do this similar analysis for turtle. Okay, we extract use a so-called PDMS polymer to extract the mixture of chemicals, all right, from the tissue, like fatty tissue, fat. Okay, and then also the turtle for turtle is blood. So we treat extracts the entirety of the chemicals, then those in the cell-based assays for every hydrocarbon, like for dioxin-like effects, and also as well as for those adaptive stress response, like oxidative stress, DNA damage information. Okay, so we also quantified a so-called persistent organic pollutants in a legacy way. Okay, so like the dioxins, pHs, PBDEs, right, PCBs. Now all those chemicals, okay, can explain very well for this specific the receptor-mediated effects, but it's still explain very small fraction of the oxidative stress. So we have seen 2 types of iceberg mixtures. Okay, so for those biologic effects that is receptor-mediated, okay, so which can be targeted by a very small number of highly active chemicals. So they can explain almost the entirety of the effect. So then this one is much easier to regulate. But for those non-specific effects like cell death, right, oxidative stress, so the unknown, typically we see the tip a very little fraction. So which means many chemicals contribute to the effect. It also triggers us to think about how to identify the unknown mixture toxicity contributors with advances of so-called effect direct analysis. But in this lecture, we won't detail it due to the time limit. As well as thinking about, now if we cannot really identify everything, then can we really regulate the mixture effects? Okay, beyond regulating the single chemicals. Now, this is also another advance, so-called effect-based trigger values, especially for water side. Okay, they're advancing, but for sediment, for biological, wildlife health and human health, it's not advancing that far. Okay, so some take-home messages. Okay, so the cocktail, although we experience very complex chemical universe, okay, in the environment, but the life it can be made easier, okay, by this kind of simplicity. The cocktail effects of chemicals in the environment, okay, follows the generally, okay, the concentration additive matter, and also mixture toxicity modeling, okay, combining chemical analysis and bioanalysis can help us to quantitatively prioritize the mixture risk drivers in complex environmental samples, okay, in marine, in a terrestrial system, okay, and also in fact, also there are two advances we need to think about. When do we need to identify the unknown effect drivers? Also, do we really need to regulate mixture effects beyond the single chemicals? Okay, thank you very much for your listening, and welcome your questions and comments. And here is my email, okay, for future response.
So thank you, Dr. Jenny. This is a very difficult topic. I would imagine some of the participants may have questions. Any question from the participants? You're welcome to drop your question in the chat box or just speak loudly. Any questions? This is still ongoing research on mixture. It's a very hot topic.
Very hot topic and very challenging topic. So also Professor Kenneth Leung is also leading a very large project on this issue, right, in the marine system. So we're looking for future, now for your funding success, okay, as well as for our future collaboration. As we also welcome the collaboration from the Southeast Asia, okay. Think about those marine water quality, okay, in terms of mixture effects, as well as for marine wildlife.
So everyone seems very quiet.
Sorry,
yes,
sorry,
please.
I have a question.
Yes, please.
Hi, Dr. Jing. Thank
Yeah,
you
please.
very much for your presentation. And I have a question about the mixture toxicity. And you talk about the chemicals don't have interactive effects. But what about the chemicals that have interactive effects? What kind of mixture toxicity model, or how can you just study the mixture toxicity of those chemicals that have interactive effects?
Oh, thank you very much, Xia Ying. Okay, so now first, I should say, from the decades of research, okay, there's one literature review summarizing, compiling all sorts of mixture effects in terms of different joint actions, okay, from synergistic effects, antagonism, or concentration addition, or independent addition. So far, we have seen synergism, okay, has very rare cases, okay, because this is actually from the an experience from the pharmacological side, okay, because they normally use only at very high concentrations, these kind of interactions or more than additive, okay, effects can happen. For example, typically for pesticides, like which I have shown this example, that like atrazine plus the organophosphate, because maybe the atrazine activates one enzyme that can catalyze the organophosphate into a more potent, more toxic transformation product. In that case, they may act together more than additive. But these are very rare examples, okay? And also think about in the environment, those chemicals are normally present in at very low concentrations. And also think about the amount of chemicals, 1,000, more than 10,000. So everything, because of this kind of dilution effect, even those things can act very strong interactively, may be diluted. Okay, very likely to be diluted in the presence of thousands of chemicals, so that they eventually may still act on a concentration additive way. Okay. And we may have further discussion later.
I think I would like to follow up. It means you support Michael Wong's proposal on this funnel effect.
Yes.
When the mixture increase to certain numbers, say 50 to 80, then they will behave just addictive, right?
Yes, I have some. Now, I haven't shown some preliminary result here. Okay, so actually I have tested up to 200, no, not 2000. Okay, 200. So starting from two binary combination, 2 components, up to 200 components. So the more the chemical the greater number of the chemical combined together, so the better the concentration additive model can predict for their joint effects.
Oh, have you published this work?
No, not yet. Not yet.
Research.
Not yet. So I want to publish it with you, okay, in support of your research.
Very good, very good.
Yeah. So, but it's very hard. Okay, we also need to have those kind of automated and robotic platform if we really want to go to thousands of chemicals.
I see. Yeah. Very interesting.
All right.
Saying, sorry, you have follow-up question, right? Saying, Dr. Xiang. You need to unmute.
Sorry. Oh, sorry. I mean, what about the microplastic and the other organic chemicals? I think
this is another issue. Okay, this is another issue. So here we're really talking about pure chemicals.
Okay.
So what you are really mean is you mean is really about multiple stressors. Okay. Because this kind of particle effects plus the chemical effects, how can we predict that? It's another level of complexity. Okay. Now also think about more complex physical chemical parameters. If temperature, right, humidity, all sorts of things on climate change or whatever. Okay, then it will be even complex. So we try to address these chemical mixture effects first, and then we go up to a higher level of complexity. But we really enjoy it and also hope to collaborate with each other in the future.
Thank you.
To develop a better predictive model.
Thank you once again, Dr. Jenny. So very, very interesting study. So we will take maybe perhaps a 5 minutes break. We will return by 3:45, 3:45. Then we will have Dr. Phoebe Warren to talk about chemical pollutants of emerging concern. So we will take 5 minutes break. Okay, I will see you return soon. Okay, we take a break. Bye-bye. Welcome back. So just for those who join us in this section, please make sure you mute your microphone during the presentation by the speaker. And also, please feel free to drop in any comments or questions in the chat box. Or during the Q&A section, you can also using the rising hand symbol or just speak loudly. Then you can give comment and ask questions to the speaker. In this session, we are really happy to have Dr. Phoebe Warren. She is a research assistant professor at the State Key Laboratory of Marine Pollution in City University of Hong Kong. Her main research areas include analytical chemistry, emerging chemicals of concern, marine pollution, ecotoxicology, and environmental risk assessment. Today, she will provide a training on the topic, contaminants of emerging concern in the coastal marine environment. Now, may I invite Phoebe to present these topics to us. Phoebe, please.
Okay, thank you, Professor Leung. And yes, is my screen okay?
Yes, you need to using the presentation mode. Yes, that's good. Thank you.
Okay.
Yeah.
Okay, thank you. So good afternoon, everyone. I am Ran Yuefei Phoebe, a research assistant professor from State Key Lab of Marine Pollution, City University of Hong Kong. So today it's my honor to join this training session, and I would like to provide an overview on contaminants of emerging concern, CEC, in the coastal marine environments. Pollution in the marine environments is widespread, it is worsening, and its geographic extent is expanding. Land-based sources account for approximately 80% of marine pollution, mainly include wastewater discharges, industrial releases, agricultural runoff, riverine deposition, and atmospheric transports. While discharges from marine shipping, offshore industrial operations, and waste disposal at sea accounts for the remaining 20%. Pollution is most severe along coastlines and in bays, harbors, and estuaries. Some of the world's worst marine pollution is seen along the coast of rapidly developing countries. For chemicals pollutants, including CEC, the marine environment is the ultimate sink, and persistent pollutants that enter the seas will stay in the oceans for years and even centuries. After they are released in the coasts, their distribution in the environments can be related to their physical chemical properties, for example, water solubility, solid liquid distribution, and vapor pressure, as well as environmental conditions such as pH, water currents, and organic matter contents. For the majority of chemicals in use today, there exists prioritization criteria called PBT assessment that is persistent, bioaccumulative, and toxic. And such PBT data are needed to establish exposure and risk threshold that protect the beneficial uses of marine ecosystems. So regarding the PBT assessment, I would like to introduce an international environmental treaty called the Stockholm Convention. It classifies the persistent organic pollutants, POPs, as carbon-based organic chemical substances that once released into the environment, they remain intact in the environment for a long period, become widely distributed geographically, accumulate in tissues of wildlife and humans, and are toxic to both wildlife and humans. And this convention requires its parties to take measures to eliminate or reduce the release of POPs into the environment. Many people are familiar with some of the best known POPs such as PCB, dioxin, PBDE, and DDT. Many POPs were once widely used during the boom in industrial production when thousands of synthetic chemicals were introduced into commercial use. Do not forget that many of these chemicals prove beneficial in pest and disease control, crop production, and industry. So here comes a new challenge due to the restriction and bans on the use of POPs. The compensatory production and usage of the alternatives replacement has led to the emergence of thousands of other chemical classes of contaminants, also known as CEC. CEC is a term to describe manufactured or naturally occurring substances that first have been recently detected in various environmental compartments. Second, are persistent or pseudo-persistent, and induce unwanted effects on non-target organisms. And third, typically are not regulated under current environmental laws. In 2016, the Norman Network, a network of reference labs, research centers, and related organizations for monitoring of emerging environmental substances, listed 966 CEC in 30 classes. Examples may include per and polyfluoroalkyl substances, flame retardants, pesticides, pharmaceuticals and personal care products, dioxide, and various proven or suspected endocrine disrupting compounds. A critical component in the ability to assess the environmental impacts of CEC is the identification and quantification of these chemicals in environmental media. We need to trace analysis techniques to address these questions. Are they there? At what levels? Can we trace them from the source to sink? But why we need to quantify trace levels? Because some CEC are persistent. They can undergo long-range transport and become widely distributed throughout the environment. Once these CEC accumulate in living organisms, they can be found at higher concentrations in the food chain at higher levels, including humans, and become more toxic to both humans and wildlife. Then, based on toxicity data, use risk assessment to propose environmental thresholds, we can answer the questions. Are these CEC at such levels safe? If not, should we restrict their production and use, or should we totally ban them? Among all, checking the levels, phase, and geographic distribution of CEC is fundamental to predict patterns of exposure, to evaluate human health effects, and to design evidence-based strategies for pollution and control and disease prevention. So in this training, we focus on two prominent groups of CEC related to POPs, focusing on their analytical methodologies and environmental behaviors. First, come to halogenated flame retardants, HFR. They are used to prevent fire hazards in products mainly made from polymers. HFR are commonly used as physical additives, and they can easily leach from products and enter the environment. Legacy HFR, such as PBDE and HBCD, exhibit PBT properties and long-range transport potential. They have been listed as POPs under the Stockholm Convention for global ban or restriction. Manufacturers have turned to the use of novel HFR as replacements, but most of these alternatives have not been verified to be safer for environmental and public health. Some novel HFR share similar chemical structures with the legacy ones, and therefore may have similar environmental behaviors and ecotoxicological effects. Recent studies have reported several representative HFR used as alternatives for the banned formulations. Their chemical structures are shown in this figure. Most HFR are neutral compounds. Accurate quantification of HFR in marine samples, such as sediments, water, and marine organisms, require highly sensitive, selective, and efficient instruments. And these instrumental methods mainly based on gas chromatography coupled to mass spectrometry, GC-MS, in the old days. Recently, liquid chromatography coupled to MS, LC-MS, and more recently, LC coupled to triple quadruple MS, LC-MS-MS. And recent studies rely more and more on the simultaneous quantification of emerging HFR using LC-MS-MS-based methods. And due to the limited availability of internal standards appropriate for the determination of emerging HFR, a wide range of mass label compounds is definitely desired. Sediment is well known as excellent sink for many classes of pollutants, and it may allow for the mapping of possible sources of pollution. Most HFR alternatives are hydrophobic and expected to be prevalent in riverine and coastal sediments. Geographic variations can be distinguished in aquatic sediment in different regions. For HBCD, which extensively reported in North America, Asia, Europe, and Africa, DBDPE, an alternative to technical deca BDE, was the most prevalent HFR, followed by HBCD. TBPH and TBB, alternatives to technical penta BDE, were found in sediments from South Africa and eastern part of China, where a lot of textile and electronic industry are found. In particular, for an emerging HFR called TBCH, High levels were observed in offshore marine sediments located far away from the territory of eastern parts of China, probably because of its long-range atmospheric transport potential. Now take our recent study published earlier in this year, for instance. The current levels and composition profile of legacy and novel HFR were investigated in surface seawater and surface sediments in the coastal region of South China Sea. 18 PBDE congeners and 8 PBDE alternatives were analyzed. Results showed that BDE 209 and its alternative DBDPE were predominant in both seawater and sediments. TBC and TTBT-TAZ, two novel HFR, were detected for the first time in the study region, and this reflects a recent pollution caused by the production and use of this HFR. A spatial shift area was observed from levels of PBDE in the vicinity of Hong Kong to those of this alternative in Zhuhai and Jiangmen, probably due to the development of industry, manufacturing household appliance, and consumer electronic products in these areas. Sediment, however, it is not able to show whether contaminants are bioavailable. The study of biota in the coastal environments can give an indication of the bioavailable fraction of pollutants and also the direct exposure to environmental pollutions. The bioaccumulative characteristic of pollutants are important parameter to evaluate the ecological risks. Commonly used bioaccumulation parameters are bioconcentration factor, bioaccumulation factor, biotar sediment accumulation factor, biomagnification factor, and trophic magnification factor. The latter two are the chemicals transferred among organisms. PBDE have been evidenced to be the substances with strong bioaccumulation potential in aquatic organisms and food web. For emerging HFR, their high lipophilicity show that these substances may have strong bioaccumulation potential. Most studies about the trophic transfer of HFR were reported in freshwater food web, and the results are contradictory and conflicted. That is, both trophic magnification and trophic dilution have been observed, and this brings great uncertainty to evaluate the bioaccumulation potential of these emerging HFR. There exists two studies about the trophic transfer of PBDE and their alternatives in coastal food web from East Asia seas, involving 31 analytes and including planktons, invertebrates, fish, and marine mammals. Trophic magnification was observed for 11 PBDE and 14 alternatives, while trophic dilution was observed for BDE 209 and 3 alternatives. TMF values have a trend of first rising and then falling against the values of KOW. This suggests that more hydrophobic chemicals have greater trophic magnification capacity. However, because of the influence of bioavailability, the trophic magnification ability of highly hydrophobic compounds may be inhibited. Higher trophic level animals such as marine mammals and birds are the target species for the global monitoring survey of POPs. Marine mammals as top predators are considered to be particularly sensitive to the effects of contaminants because of their relatively long lifespan and specific tissues such as blubber and liver that allow the bioaccumulation and integration of lipophilic or hydrophobic compounds. Blubber is a layer of fat tissue under the skin of marine mammals, where most lipophilic contaminants, such as HFR, are bioaccumulated. These figures show a global comparison of the baseline concentrations of several PBDE alternatives in the blubber of marine mammals, including dolphin, porpoise, whale, beluga, and seal. HBCD was the most intensively investigated in the marine mammals from North America, Asia, and European seas, with the highest levels found in harbor porpoise from UK. The second most studied PBDE alternative is Decoran Plus, with the highest levels found in Indo-Pacific humpback dolphins from South China Sea. So take our recent study about marine cetaceans, for instance. Two resident cetacean species, as mentioned earlier, finley porpoise and Indo-Pacific humpback dolphins, were susceptible to exposure to high levels of HFR. Our research findings suggest the increasing use of most PBD alternatives in the South China region following the restriction of the production and use of PBD technical mixtures. HBCD has been listed as one of the POPs since 2013, and then its production volume in China has been decreasing. These chemicals show an increasing trend in dolphins with an estimated annual rate of 8%. This evidence the high persistence of HBCD in the environment. TBCH is one of the alternatives for HBCD. The higher increasing trend of TBCH in dolphins indicates a possible rapid growth in the TBCH consumption in the Greater Bay Area. So in summary, HFR were found to be widely distributed in the coastal marine environments, such as some Chinese coastal regions. However, data for emerging HFR are still far from enough, especially other regions in the East Asian seas. Further studies are needed in a variety of fields, with a focus on contaminants monitoring, environmental behavior, toxicokinetics, biodegradation process, and ecological risk assessment. Next, come to per and polyfluoroalkyl substances, PFAS. They have fully or partially fluorinated carbon chains. They show excellent biochemical stability and high surface activity, and they are widely used in our daily life, such as in firefighting foam, food packaging, and ski wax. PFAS are highly persistent in the environment, and this has resulted in their worldwide occurrence even in remote areas, such as polar region. Two legacy PFAS with A carbon chain length called CA-PFAS, that is PFOS and PFOA, show persistent bioaccumulative and toxic properties, as well as long-range transport potential, and therefore have been listed as POPs for global restriction and ban, respectively. Short-chain PFAS and PFAS with similar structures have been manufactured as alternatives. These emerging PFAS have similar physical, chemical, toxicity, and bioaccumulative properties with the legacy ones, but they have not been studied as much. With the increasing availability of high-resolution MS systems, more important progress have been made recently in the detection and identification of previously unknown PFAS. The chemical structure of some selected emerging PFAS are shown in this figure. Unlike HFR, most PFAS, including the emerging ones, are ionizable, and the majority of them are anionic compounds. For ionic PFAS, LC-MS with negative electrospray ionization in multiple reaction monitoring mode is used for quantification. One important concern is the background contamination, and particular attention should be paid to auto-sampler vial caps, tubing, solvent inlet filters, and a variety of other lab products containing fluoropolymers. Precaution measures can be made, such as using polypropylene vial caps and installing a guard column or trapping column prior to the injector. For neutral volatile PFAS, GCMS with positive chemical ionization in the selected ion monitoring mode is used for monitoring. GCMS can also be used to determine ionic PFAS, but the time-consuming derivatization procedure is required. This figure shows a global comparison of PFAS in the water, sediment, and organisms in the estuarine and coastal regions. Study found that PFAS are worldwide detected, and the proximity to source and determines the distribution of PFAS, followed by environmental factors such as salinity, pH, and precipitation, as well as the physicochemical properties of PFAS. In particular, evidence shows that there could be a proportional relationship between the increased salinity and increased bioaccumulation, as well as partitioning to sediments. In marine food web, similar to the findings of HFR for PFAS, although most investigated PFAS are biomagnified, both trophic magnification and trophic dilution have been observed. So as mentioned earlier, marine mammals are one of the target species for the global monitoring of POPs. Unlike many POPs, which are both hydrophobic and lipophilic, PFAS are hydrophobic but lipophobic. However, they are proteophilic. This means PFAS show high binding affinity to proteins. And therefore, liver is one of the target organs for PFAS bioaccumulation in animals. Take our recent study published earlier in this year, for example, including finny porpoise and Indo-Pacific humpback dolphin. The global restricted PFOS was the predominant compounds in our cetacean liver samples, accounting for nearly half of the total target PFAS levels. 622 co-related PFESA was the second most predominant PFAS, accounting for nearly 1/3 of the total PFAS levels. This suggests 622 co-related PFESA, an alternative for PFOS, may have a similarly high bioaccumulation potential as the restricted PFOS does. We found increasing levels of PFHSS in marine mammals. This chemical is a 6-carbon PFAS, and now it is under review by the Stockholm Convention. Increasing temporal trends were also found in levels of 2 emerging PFAS called PFECHX and HFPODA in finny porpoise. These 2 chemicals have been used as PFOS and PFOA alternatives respectively. These indicate an increasing use of them in the Greater Bay Area, especially Hong Kong. Both porpoise and dolphin are ecologically important marine species. Ecological risk assessment of marine mammals exposed to PFAS can be performed based on the measured PFAS level in the liver. The toxicological data for cetacean species were lacking, as we cannot really dose the living cetaceans with PFAS. Therefore, a toxic threshold called tentative critical concentration, TCC, for cetaceans were derived from toxicological studies on other mammal species, such as rodents. We use hazard quotients, HQ, to preliminarily quantify the risk. HQ is the value of measured environmental concentration divided by TCC. And HQ higher than 1 indicates that this cetacean under PFAS exposure could suffer high health risk in terms of reproductive injury potential. So here, I would like to pay emphasis on 622 co-related PFESA. We found approximately 80% of dolphins and porpoises could suffer high risk from exposure to this chemical. Therefore, control measures for this emerging PFAS are urgently needed. Ecotoxicity data for most of the reported emerging PFAS are not available. And that is to say, more study on environmental behavior and toxicological effects of emerging PFAS are required. In the final part, I would like to introduce a novel analytical approach called non-target screening. According to the OECD database, to date, there were approximately 5,000 commercialized PFAS. However, typical environmental analysis tend to focus on analyzing specific chemicals of interest, that is target analysis, as mentioned earlier by Dr. Jingling. These are confined to a limited number, mostly not exceeding 100 compounds. High-resolution MS, such as the quadruple time of flight MS cutoff, has been successfully applied by using non-target screening. And this allows the identification of unknown compounds without requiring any prior information, such as reference standards. I used 1 dolphin liver samples, for instance. Raw data in QTOF contain over 10,000 pigs. After potential PFAS homologs were shortlisted by a mass difference in CF2 units, we found around 1,000 PFAS candidate left. Next, we restrict the mass defects, and nearly 400 candidates were left. Then we retained the candidates, showing increasing trend between the retention time and molecular weights, and then only around 100 candidates were left. Finally, we checked the isotope and MSMS results of the candidates one by one, and 36 PFAS were identified in these dolphin liver samples. Using our non-target screening workflow, additional 44 PFAS from 9 classics were newly identified. Finally, current efforts to develop analytical methodologies for novel and unknown PFAS are still inadequate, and more efforts are needed to develop a robust approach to the investigation of and comprehensive analytical protocols for these contaminants of emerging concern. So that's all for my presentation. And if you like for a further communication, and here is my email. So thank you.
Thank you, Phoebe, for the very comprehensive overview on the monitoring of this group of emerging chemicals with examples. So we see the first question from Jamaica. She is asking, what particular brand of LC-MS was used in your study?
Yes, LC-MS, we use the Agilent LC and coupled to the SciS 5500 MSMS is a Q-chap.
Maybe I invite Jamaica, maybe you can switch on your videos and you can have a direct discussion with Phoebe.
Yes, welcome.
Yes, you can unmute Jamaica. Please feel free to discuss now. And also we welcome other participants to join the discussion. Dr. Jennings, you have a question? Yes, please. Yes, we can hear you. No problem.
Oh, no. Sorry, because I just returned from another meeting during this time. Okay, sorry, I just sat down. Okay. Yeah, maybe leave the audience to ask. I may have some follow-up later.
Okay, Jamaica says she is working in the lab now. Cannot see you. Okay, any other questions from the floor? I think Phoebe also welcome collaboration with participants from the East Asian Sea area.
Yes, because most of the environmental data for these emerging contaminants are lacking in most Asian Sea area. So yes, more collaboration are welcome.
We also look for a stranded dolphin sample. If you have any, please send to us. So Francis also asked a question. Other than marine mammals, are there other animals that are object of study for accumulation of this CEC? Yes, please. What are the target species we can use?
Yes, take our investigation in Hong Kong waters, for example. We collect invertebrates, including mollusks and crustaceans, and also fishes to compose whole food web. And as mentioned earlier, we found the trophic magnification for most of the HFR or PFAS investigated. But for some of the other emerging PFAS, we also observed trophic dilution. So yes, for the marine food web, we can see the bioaccumulation of most investigated contaminants in crustaceans, mollusks, and fishes, especially those at higher trophic levels.
So Francis, do you have follow-up question? Please feel free to turn on your microphone and discuss directly. Could you see the correlation between the, I suspect, correlation seen so far? Do you mean the correlation with the food web or correlation with different species? Francis, maybe you can switch on your microphone and give us more.
Yeah, maybe you can talk.
Yes. Oh, for different species, you mean? So are there any correlation being seen so far for different species?
Perhaps you ask is the trophic magnification, is this a term that might be not so clear to you?
Mm-hmm. Okay, I also see Caesar, would you like to ask a question? I just see he just turned on the video. Yes, please. Yes.
Dr. Wang, actually, I came back late, so I didn't catch the entire presentation of you. But my interest is, if it's difficult, like I saw that you have only one sample of the dolphin, so maybe in the lower in the, or in the other parts of the trophic structure, you can already see, you said there can be either dilution or there can be magnification depending on the species, I hope, or their position in the food web. So that at this point, or at this point, do you already have some maybe more how do you call it, more a better view of for example, if you have this amount of PFAS in one in one trophic level, or in one species, which is part of the food web, can you make some prediction or projections on the values of the rest in the food web, something like that, for modeling purposes, maybe?
Prediction and modeling.
Oh, you mean if we know that the bioaccumulation factors or something, can we using this value to predict whether specific species at certain trophic levels, that we can know how many? Yes, because so when you have a whole food web species, then maybe you can contain like tens of or 20s of species occupied at different trophic levels, from the planktons to the medium trophic level or high trophic level fish, and even marine top predators. And then you can obtain, like do the correlation, linear regression, and obtain the trophic magnification factors. And then using these factors, if the species is also from the same food web from your study, and then you can use this linear correlation to calculate the exactly TMF value of this species.
Yeah. So is that possible at the now, given the available research information?
Yes.
Okay. So the main thing that you are, for example, targeting for collaboration among places in the rest of the Southeast Asia is the gaps.
Yes, a very important gap.
Yeah, so have you identified it so far? Which are areas of priority for you, for that particular type of research, or toxicant or something?
So sorry, pardon, I do not quite understand the question.
So if you have identified the gaps geographically, can you now like perhaps prioritize which places in the Southeast Asia are missing in have a important contribution to the missing parts in your story about emerging contaminants?
Yes, because most of the study found in East Asian Sea are from Chinese coast or Japan or Korea, and then we lack data, especially those from Southeast Asia, like Philippines, Thailand, and the marine food web. The contaminant status of the marine food web is unknown to us currently.
So it's the entire East Asian Sea. So I also received a question from the internet. So from Demika, she said this is a very timely presentation because we will be working on a similar study here in Philippines, as well in our local river water using similar instruments as what was used in your study. Did you go as low as 2 ppm for the mass error during data analysis? It's a technical question.
As low as 2 ppm, you know the mass resolution. I think for the LCMS, because we use not the high resolution but the regular function. So actually we get as low as like 10 ppm the mass error. But if you use for the high resolution MS like QTOF, then the mass error should be as low as 1 ppm.
So in our laboratory, we have many different advanced instruments. We just install the GC Orbitrap, very highly sensitive instrumentation. If you need our contribution, we are very welcome to collaborate with you. Then we can arrange for shipment of the samples to our lab. Then we can do the analysis and publish the result with your team. Yeah. Then Jamaica, another follow-up question. Did the instruments have a library?
Yes, our QTOF or Orbitrap has already purchased several libraries, like for pharmaceuticals or for forensic compounds or even for algotoxins.
Okay, so we have a quite extensive discussion now. So because of the time, then we will move on to the next talk. I pass to Dr. Once again, thank you, Phoebe, for the sharing. Then now I pass the MC position to Dr. Jenny.
All right, yeah, so, okay. So today we have a very wonderful program and talking from spanning from environmental management, risk assessment, communication and management, as well as some paradigm shifts of the. So then Professor Leung will give us an introduction of his grand project. Okay, really grand project endorsed by the United Nations. Okay, so now let's welcome Professor Leung. Thank you.
Oh, thank you, Jeannie. Can you see the screen?
Yes.
Okay, good. So this presentation is a pre-record. So then I hope you enjoy. It will take around 18 minutes. Okay, let's start. Before my talk, I would like to make an advertisement of our
Yes, it's clear.
Regional Studies in Marine Science, which was launched in 2015. We are very pleased to see its healthy development. Now with an impact factor of 1.624, we welcome any good quality manuscripts of regional studies in marine science. Okay, in this talk, I will discuss about the major threats to our ocean, the problem of marine pollution, and how global initiatives can solve this problem. I will also introduce some new global initiatives. Concurrently, our oceans and marine biodiversity are facing 6 major threats, which include climate change, habitat loss,
pollution, biological invasion, overfishing, and diseases. Marine pollution is one of the major threats. More recently, inadequate governance that leads to more habitat loss, more pollution, and overfishing is also regarded as another threat to our oceans. So we do need to tackle marine pollution. Improving water quality, in fact, will also bring many benefits to our society. Clean water is vital to not just marine biodiversity, but also our survival. It is because a healthy ocean can provide a stable climate and a marine ecosystem that offers what we need, such as oxygen for us to breathe and safe seafood for our consumption. In addition, the ocean also supports our recreation, tourism, and blue economy. However, the problems of marine pollution is very complex. It was estimated that 80% of marine pollutants came from land-based sources, which consist of both pond and non-pond sources of pollution. The latter is more difficult to deal with. With the globalization, there are movements of natural resources, products, and waste across countries through international trade. So to speak, pollution has no boundaries and will require international collaboration in solving this problem. Now, I would like to ask, why are global initiatives important to tackle pollution problems? There are a few very successful cases which emphasize the There are a few very successful cases which emphasize the importance of science policy interface, using science to support policy formulation and informed decision-making. The recovery of ocean depletion in stratosphere is one of the best examples. First, scientists discovered the depletion of ocean layer due to the release of chemicals like chlorofluorocarbons. Then scientists educate the policymakers and propose to globally ban the use of these chemicals. With the support from UNEP and joint efforts from many countries, we see a sharp decline of these ocean depleting chemicals, and at the same time, we see the progressive recovery of our ocean layer. It is a very happy story indeed. The second successful story was the ban of the use of organotin compounds in anti-fouling systems, leading to population recovery of marine oysters and gastropods around the world. More recently, the global effort in achieving plastic-free oceans successfully triggered the ban of single-use plastics in many countries. So, scientists need to do good science, and at the same time, we need to educate policymakers. Scientists can help policymakers to answer regulatory questions and even conduct research studies to address their needs. Science policy is often based on evidence generated from high-quality scientific research. As you may know, the United Nations has declared a war against ocean plastics since 2017. Since then, there have been many global initiatives and campaigns to fight against plastic pollution, such as plastic-free oceans, leading to very good results that many countries have now banned the use of single-use plastics. In contrast to plastics, chemical pollution has received comparatively little attention from the general public around the world. Nevertheless, the UNEP recognized the importance of managing chemical pollution and has published 2 volumes of the Chemicals Outlook.
In the chemicals outlook, UNEP would like to strengthen the science policy interface and the use of science in monitoring progress, priority setting, and policy making throughout the life cycle of chemicals and waste. In early this year, a group of scientists published an article in the Policy Forum in the journal Science and called for establishing a global science policy body on management of chemicals and waste. Such a global body would be similar to the Intergovernmental Panel on Climate Change, IPCC. This body should be an inclusive one with members from various sectors from both developing and developed nations with a gender balance. This new governing body will be able to foster joint international action to reduce chemical pollution. Apart from the initiative of UNEP, private sector has also launched some global projects to protect our oceans. For example, Back to Blue project is initiated by the journal The Economist and the LePont Foundation in Japan. These two organizations realized the need to improve evidence-based approaches and solutions for ensuring ocean sustainability. They found that 83% of the general public are concerned with issues affecting the ocean. Back to Blue focuses on 3 issues, namely plastic pollution, chemical pollution, and marine biodiversity. They would like to transform scientific knowledge into solutions that address pollution issues. The Economist will be able to bring the issues to wider audience and stakeholders with a view to encouraging the public, business, and governments to work together to solve these issues. The team of Back to Blue has been working with experts across the world. I have been serving as a member in their expert panel to explore different ways for achieving zero chemical pollution through governmental and financial interventions, advancing policy at national and international levels, while seeking contributions from various stakeholders. Let's see an example. The team of Back to Blue invented a plastic management index and applied it for 25 selected countries. Here, taking China as an example, the index comes with a score of 63.3 and a rank of 10 among the 25 countries being tested. Most importantly, the index comes with a breakdown of scores in governance, systemic capacity, and stakeholder management, from which areas for improvement can be identified. Through this index and benchmarking, this can promote the best practices and point to areas for improvement. If every country can make advancements in their score, the global plastic management will be ultimately improved. However, the entire process is on volunteer basis. That active engagement of the country is not guaranteed. The most exciting global initiative for ocean sustainability is the United Nations Decade of Ocean Science for Sustainable Development, which has been officially launched since the 1st of January in this year. The United Nations want to provide a platform to support efforts to reverse the cycle of decline in ocean health and gather ocean stakeholders around the world to ensure that ocean science can create improved conditions of our oceans. There is a slogan, the science we need for the ocean we want. So in December 2020, the United Nations called for proposals from the global ocean community, allowing stakeholders to plan for the decade of ocean science research and activities for promoting ocean sustainability. Concurrently, there is also the UN Decade on Ecosystem Restoration with a focus on habitat restoration. However, the governance structure of the Decade of Ocean Science is rather complicated. This global initiative is under UNESCO IOC, in which there is a decade coordination unit for managing this initiative. There is a decade advisory board, which mainly evaluates proposals from the ocean community and gives professional advices. In each December, there is a call for proposals, and then the advisory board will evaluate the proposal and make recommendations for UN to endorse. There are 3 types of proposals, including Decade Action Program, Project, and Activity. Projects will be under a program, and both projects and programs will be under a community of practice. The system would encourage more interaction and collaboration, as well as information sharing among different groups and stakeholders. For example, our proposal on the Global Estuary Monitoring Program was submitted in January this year. It was selected and endorsed by United Nations on the 8th of June this year. Our program is under the Coastal Ecosystem and Community Resilience Community of Practice. 3 weeks ago, a new project called Estuary Ecological Knowledge Network was endorsed by UN and assigned under our GEM program. It is because this project is highly relevant to estuary monitoring. Concurrently, our separate proposal on turning our international conference series on biodiversity, ecology, and conservation of marine ecosystems into a decade activities was also approved. This BECOME conference will be held in hybrid mode during the 3rd and 7th of January 2022. The deadline of abstract submission is on the 3rd of November this year. You are most welcome to join us. For more details about the conference, please visit our website. In the final part of my talk, I will introduce the details of our GEM program. Our GEM program was inspired by the Global Monitoring of Pharmaceutical Project, which was created by Professor Alistair Bossell from York University in the UK. He and his postdoc, Dr. John Wilkinson, developed standardized methods for sampling and chemical analysis. There were sampling kits, training materials, and video for partners to ensure the sampling in order. Ocean samples were then returned by courier service to York University for analysis. They successfully developed a powerful analytical method which could measure 60 target chemicals with just 5 milliliters of water sample. The project successfully engaged researchers from 102 countries and mobilized them to collect samples from 252 rivers around the world. Given the simplicity of the sampling, people from developing nations could also join the project, enabling capacity building. The results of the project are very meaningful because we can identify polluted rivers, geographical patterns of pollutants, priority pollutants of concern, and the relationship between pollution intensity and socioeconomic status of the country.
The results provide insights into developing strategies for improving water quality in global rivers. Initially, our GEM program is just an extension of Professor Botso's project, extending from global rivers to global estuaries. With more partners and funding support from the City University of Hong Kong and the National Marine Environmental Monitoring Center of China, we will be able to do more in the future. We will develop standard methods for sampling and chemical analysis, and then invite partners to carry out the sampling. We will conduct all chemical analysis at our laboratory in Hong Kong. We will also derive predicted no-effect concentrations for target chemicals and use them for benchmarking and conducting ecological risk assessment. We will share the results with partners and stakeholders, and most importantly, will deliver solutions for improving the water quality that will hopefully lead to cleaner and safer estuaries for all. In the next phase of GEM program, we may include monitoring of contaminants of emerging concern by using passive samplers. We could also monitor microplastics, pathogens, antibiotic-resistant genes, and environmental DNA in seawater, sediment, and biota. Tentatively, we plan to deploy our artificial muscles for monitoring heavy metals and deploy organic DGT for capturing targeted contaminants of emerging concern. We have started to collect oysters from different parts of the world and use them to monitor microplastic and pharmaceuticals in coastal waters. We are very excited about this global initiative, and we welcome any of you who will be interested to join us. For more details, please visit our website or email us. In conclusion, I hope I can convince you that we really need concerted global effort to tackle marine pollution issues and to promote ocean sustainability. To further improve the management of chemicals and chemicals pollution, a global body to provide a science policy interface will be essential. From the past experience, good science can help develop good policy and solutions to tackle environmental problems. With more and more global initiatives like Back to Blue and Decade of Ocean Science, I'm very positive about the future of our oceans. Thank you very much.
Okay, so in the last part, I would like to initiate the discussion section, and I would like you to provide us some idea. If we're going to organize more training workshop like this one, what kind of topics you would like to hear from us? Then please go to Slido through this website, app.sli.do, and then enter this code 851423, and then you can fill in this questionnaire. Then we will combine the result and show you the work how, and then see in the future development of this training workshop for the region. So once again, thank you. Then I pass back to Jenny.
Yeah, this is a really great global initiative. We really welcome students and experts, okay, all around the world for concerted action together for the ocean decade. Okay, all right. So here comes to the final part of our today's training. So I'd like to invite all lecturers and participants to join a roundtable discussion. All right. So our trainers today's Professor Kenneth Leung, Professor Rudolph Wu, and Professor Professor James Fong and Phoebe, all right, as well as myself. Yeah. So as well as a lot. We still have how many? Loads of participants online. Huh? So yeah, please feel free to ask questions if you haven't come up with in the front. Okay.
So
okay.
I already put up the link of Slido, and also you need to fill in the keyword 851423, and then you can fill in any topics you'd like us to teach in the future workshop. We are also very welcome any questions about today's lectures and also about the global initiative I just mentioned.
Yeah, any feedbacks are welcome. Feedbacks, suggestions, questions related to today's lectures or whatever. Okay. Also, feel free to contact us, okay, in the future correspondence if you have any questions or feedback as well.
Professor Kenneth Leung?
Yes.
May I please ask the first question about the global project? When will we start the first sampling, and how do the interested collaborators join the monitoring program if they want to?
So this is a very good question. We will call for membership in December. Then in our website, we just show you, you just need to Google Global Estuary Monitoring, then you will see our website. We're going to post a link there for application. Then all interest parties just need to fill in a form to see your sampling capacity. For example, whether you have a boat, whether you have a grab so that we can get sediment sample, whether you have a refrigerator to frozen the sample at -22°C and so forth. We ask you a list of questions and then see what kind of project you can contribute. The project level is from data collection for making a review article to all the way to very complex experiment. Then we're looking for different types of partners. The complex experiment, for example, we will ask you to deploy the passive samplers for a given time, say 3 months. Then you have to collect the sample for us every month. Or like to support your project to collect oyster from different parts of the world. We also build in inside the questionnaire, the people can help. Then once we gather the information, then we also need to look at the geographical coverage. We would like to target to 100 to 120 major estuaries in the world. Then we will select a different group of people to cover different areas. So this is the idea. We're still working on the standardization of the method. We are hoping the first batch of sampling will be talking about water sampling will be start around April, May next year. And then meanwhile, we already tried to invite people to send you the oysters. But due to COVID, the transportation having some hiccup right now.
Yeah, I see. Thank you, Professor Leung.
You're welcome. So if maybe meanwhile I can show the Slido result. If I can share the screen again. I think sorry, the Slido here. Can you see the screen? Then
yes.
We already received some topic: remediation of pollutants, 2 volt, watershed management, status of Antarctica. Wow, this is a very specific project. Expedition in Antarctica. expensive, transformative approaches, elaborate digital solution, Antarctica research, microplastic pollution, nutrients loading swine, and this related to the pig farm, I guess, microplastic monitoring. I think those are good suggestions. We also have a distinguished researchers a seminar series. It is possible to bring someone leading authority working on Antarctica pollution problem. This could be done through our State Key Laboratory of Marine Pollution. Just want to see with this topic, any feedback from the speaker, Phoebe, James, and Lathan?
So may you please say again your question, Professor Lam?
So these are the suggested topic for future training workshop. Just see whether you think those topic you can help, especially microplastic pollution. It seems many audience interested in your study. Maybe we can expand to a half-day to one-day workshop just dealing with microplastic.
I see. We are doing microplastic in our lab. Currently, we are using Raman spectrometry that I have presented in the presentation. We have recently got more advanced equipment that allow us to analyze microplastic down to close to nanoscale at 400 nanometer particle, which is a good advance to do science. So in the future, I will try to develop a method and we'll report to the audience how we can do this.
Oh, very good, very good. So I think people also suggest non-target LCMS analysis. Phoebe, would this possible to organize a training workshop or the seminar series on this topic?
Yeah, I can organize a seminar like this.
On the non-target analysis. Okay.
Yes.
Yeah,
Ken has an overview and performing several reviews and providing the basic criteria of this non-target screening.
Yeah, I stop sharing. So I would like to invite the participants to ask questions or share your feelings about today's workshop. Do you enjoy it, or you feel some area could be improved and so forth? Please feel free to voice out your feedback. We would like to hear from you so that we can further improve. We plan to organize this cup training at least once per year or even twice per year with a specific topic in the future. Okay.
Yeah, President.
Yes, please.
Yes, just following up your question. Okay, I also specifically want to try to understand. Okay, the needs. Okay, any needs from the Southeast Asian countries in terms of marine or broadly environmental protection management, so that we can contribute somehow in some technical aspects to help them address some problems. That's why
we can invite Daisy. Daisy, would you mind to answer this? What is the need, or what are the needs of the region?
Any specific needs, for example, from Philippines in terms of technical capacity building, or any specific environmental issues that you encounter that would like us to help with, for collaboration or somehow.
Yes, Daisy, are you one? Would you please share your thoughts with us? Thank you. Yes, please. Thank you.
Thank you, Professor Leong, and thank you, Dr. Fang. Yeah, actually, it was the topics actually was very diverse from this morning until this afternoon. So covering risk assessment, risk management, to more technical research on specific pollutants and microplastics. I think there are several opportunities for collaboration, especially with our network of learning centers. I think we have some here, UP Visayas, and then I think we also have De La Salle Lipa. In one of the last the presentation of Professor Leong on the global research for estuaries, global monitoring of estuaries. Actually, we are encouraging our partner universities and even the local governments to visit the website, and then maybe they can participate in the monitoring initiatives. We can check on the website and see how they can be part of it. They can just collect samples and then send it to Hong Kong, or maybe to the lab, and then we can have a fuller understanding of the quality of the different stories in the regions. And then for some universities, maybe they have also specific needs. We have a current project, the ASEAN Norwegian project. They are also looking into plastics monitoring. So maybe there can be potential collaboration in terms of the methodologies on plastics monitoring, microplastics monitoring. So maybe we can, in the future, like organize a training or sessions to work or to discuss the different methodologies for possible standardization maybe, or sharing of methodologies and all that. So yeah, we can have discussions maybe later on possible training that we can conduct with the different universities and maybe local governments. So we'll check what specific needs they would require that the universities from Hong Kong can provide. Yes, and I think there are many opportunities for possible collaboration with the universities. And thank you. And I think we can ask some of the participants, maybe Frances, and from De La Salle, maybe from Batangas also, maybe they can share what they think are possible opportunities for collaboration with the universities from Hong Kong. And maybe UPLB also, Hildy. So we can, as one of the output from this seminar, maybe a potential partnership or collaboration from the participants and then from the universities in Hong Kong. Anybody?
In this sense, we also really welcome personal exchange, right? So it may send some staff or student or interested parties to Hong Kong, right? To for collaboration, also convey of this kind of technical training or whatever. So for the mutual benefits. Right?
Yes, we see Francis. Please speak up. Yeah.
I have already sent by email. I tried to browse through the GEM website, but I think it needs a little bit more time to absorb everything. And I can see, I cannot see actually what you showed us. There's a.
We have yet to launch the call for.
Okay. but I did email Dr. Leong already for intent to collaborate, at least in behalf of our station in Guimaras, where I'm currently station head. But you see, in our campus is also located in Iloilo City, where the main, I think the center of our activity is estuary, the Iloilo River estuary, so to speak. So I think this is very relevant topic for us.
Yeah, we welcome more collaborators like you. So we are very inclusive project. We try to gather people who are interested in this topic and working together for the good of the ocean.
Yeah, but also aside from the more equipment, high-end equipment requiring activities for monitoring, do you have also citizen science thing, cheaper version, but still useful monitoring protocols that are can easily be done by locals and can be done here using simple equipment?
I see. Why now we are developing some weapon detection kits for antibiotic residues. If the project is successful, then we will distribute this weapon detection kit to different parts of the world. Then the assays only take 3 hours to get result. You can send the image of the color changes through a online platform so that we can gather the global data together. But this may take 1 or 1.5 years to develop. We dream about it. We want to have some very simple kits. Even just school kids can help to collect data. This is the way forward. So you point to a good direction. Right now, the water sampling also very simple. We will set up a video training and also online training for all participants. I think you just need a refrigerator at -20 degrees or lower, then to keep the samples before the DHL or the FedEx come to collect the samples. Otherwise, I think the requirement for the partner is very low for this. But we also have very complex experiments like those using passive sampler that will require more facility the partners should have. Yeah, thank you, Francis. So any other questions or comments from audience? You can also type in your suggestion in this chat box as well, other than the Slido. Okay. So if no more questions, may I invite Phoebe to introduce?
There's one,
yes.
Professor Long, in the chat box. There's one question.
Okay, good.
From Miss Hildy.
Okay. Oh, she wants to study the inland water as well. So in the estuary project, we're going to have a chance that in each estuary from the river mouth all the way to open ocean. So then we will cover the little bit of inland waters as well. So if they want to measure the inland water, if they have extra bottles, they can send to us. We will be able to analyze for them as well. So then more details we can sit down and talk about the sampling design and so forth, yeah, in the later stage. Yes. So thank you. So now may I invite Phoebe to showcase tomorrow program so that everyone can prepare for the tomorrow program better. So Phoebe, please.
Right. So for tomorrow's program is symposium that will begin at 8 o'clock for Cambodian time and 9 o'clock for Hong Kong time. And so for those registration for registering, you already received the email and also the latest program rundown. And So may I show about the program here or?
Yes, please. Yeah.
Okay, just a moment, please.
Meanwhile, James, there is a question for you, whether or not you can collaborate with students from overseas to teach them how to do the microplastics survey. It's in the chat box.
Okay. This is a long question. Let me read.
From Catherine, yeah.
Okay.
Yeah, Catherine.
Yeah, sure.
Catherine is here, so please speed up. You need to unmute, Catherine.
Yeah, sure. Collaboration is very welcome. Currently, what we do with the collaborator in Japan, Korea is we send a standardized sampling kit to them to make their process easy. They collect the microplastic from the biological sample, then they send us the stainless steel filter membrane. We collect the membrane, then we analyze the microplastic, which the process has been established.
Okay, so perhaps James, you can make a video and teach them how to do it, and then maybe send the kits to them, then they can help. I think this is a good collaboration.
Yes, I agree.
Other groups also can join this global initiative. Yeah. So on behalf of the organizing committee, we would like you to fill in the questionnaire to provide us some feedback for today's training. So it's in the chat room. Grace just sent out the link. The form, please fill in the feedback form for us. Won't take you too much time, only 1 minute. You can fill in the form for us. Thank you for your help. So Phoebe, please.
So do you mean this rundown?
Yes. Tomorrow. You need to enlarge it to a bit smaller.
So for the morning session, then we have several speakers. Then we will last to 12 p.m. in Hong Kong time, and that is 11 a.m. in Cambodian time. And the same as today, we will have 2 hours lunch break. And then in the afternoon, we also have several presentations. And then for the final parts, we will have a panel discussion that will start it at 4:30 p.m. That is 3:30 p.m. in Cambodian time to discuss about the growing challenge of marine environmental research in East Asia, and welcome everybody to join.
Tomorrow topics will cover antibiotic resistant genes from Professor Jiang Tong, and also look at climate change impact to ecosystem restoration using eco-engineering, and also 3D printing for corals, farming. So tomorrow will be much wider scope. As I said before, we are developing rapid sensors for detecting antibiotics. Then tomorrow, Dr. Kok will talk about this issue, the new technology. Professor Wu will also discuss about the problem of hypoxia, dead zones in the world. Then we will cover some very new topic, like the liquid crystal monomers. Those chemicals come from our mobile phone. So how far they reach into our ocean, what is the impact to human, then we will have a discussion. So tomorrow we will present many latest discoveries. Today we provide the concept. Tomorrow we will focus on the latest research. So please do join us tomorrow. So finally, once again, please fill in the questionnaire we just post up on the chat room. I think Grace will also send you the link through emails later. So thank you all the speakers. Thank you all the participants. Thank you very much. Have a good night. Bye-bye.